Now we've got our data in batches, but it could be a little bit hard to understand what's going on in a batch. So let's build a little function which is going to explore what's in our batch so we can visualize what's happening. Because if we have this little output here, we know deep down that these are actually images and these are labels. It would be good to see them. So let's make a little heading here, visualizing data batches. Command MM to turn it into Markdown. And let's give ourselves a little bit of communication. Our data is now in batches. However, these can be a little hard to understand / comprehend. Let's visualize them. Because I'm not sure about you, but I like to see things in action. So to do that, we'll import our trusty matplotlib. Look at that, auto suggestion. And then we'll go create a function for viewing images in a data batch or a data batch data. We Australians, the Australian accent, like to throw R's onto the end of vowels wherever they are. We might do it, just show 25 images, because if we're doing too many, like we have 10,000 plus, so we might just show 25 at a time. And we want images and labels, because what we're going to do is basically plot an image and then above it put the label. And nice and simple, we'll go displays a plot of 25 images and their labels from a data batch. Wonderful. All right, so let's set up the figure. We'll go plt.figure. We'll make it fig size. Now I've had a little bit of experience with setting up this plot size, so hopefully 10 by 10 is good enough. If not, we can change that. Then we'll go loop through 25 for displaying 25 images. So we'll just set up a simple loop. We'll go for I in range 25. Then what can we do? Well, we need to create a subplot. Let's make it 5 rows, 5 columns, because that's 25. And then we'll have to display an image on each of the subplots and then add a title to each of the images. Well, that shouldn't be too hard. So create subplots. We'll go 5 rows, 5 columns. Go ax equals plt dot subplot 5 I plus 1. So this is, it's because we haven't imported matplotlib yet. That's why the docstring isn't showing up. There we go. Parameters. Where do we got? It got rows.column. So this is number of rows, this is columns, and this is index. That's all you need to know. Display an image. Some of the matplotlib docstrings can be a bit annoying, like when they go args, keyword args, and it just inherits off some other class and you can't really find it. If you need to check out what this actually does, check out the matplotlib full-blown documentation. We want to plot the ith image. So because we're looping through, this is going to be a data bunch of images and labels. So we want to show the ith image. So the ith index. Am I saying that right? The ith image. Add the image label as the title. So we'll go plt.title and then unique breeds, because that's our list. Remember, if it still lives in memory, it should. Unique breeds is our list of unique dog names. Get the unique breeds label. We want to index that where labels, the ith label is the maximum value. So in other words, if we go y0 argmax 19, this is just exactly what we're going to be doing with that line up there. Unique breeds. So this line here is the title of our plot. Boom. See what I mean by defunctionizing functions to really explore what's going on? So if you want to figure something out, remember, always you can just pull the function apart. Rewrite the code for yourself, because that's how you're going to understand something. Turn the grid lines off. Actually, we might see it with them on before, so we know exactly what this is doing. plt.axis. That's a nice simple function. Show 25 images. What do we need to do now? So because our data is in a batch, we need to essentially unbatch it to visualize it. So we can do that by going train images. Let's see the code first, then we'll see what's actually happening. Train labels equals next. So what next is it returns the next item from an iterator. Oh, well, thank you, docstring, for that. Because train data is in the format of a batch, so if we go train data, we need to turn it into an iterator. There we go. So we can do that by calling the method as numpy iterator. And what's this going to say? Returns an iterator which converts all elements of the data set to numpy. So basically what this is going to do is turn... Oh, there we go. We got some information here. Those doc strings are a little bit hard to read there for me. But let's just go through here. What's it going to do? So it's going to take our batch data set. It's going to unwind it from a batch and turn it into a numpy iterator. And then thanks to next, it's going to grab the first batch off the top of this, out of this iterator. And then because it's split it, it's unbatched it, training images, so this one here, this shape here, is going to be the first thing that gets returned. And train labels is going to be the next thing that gets returned. So don't take my word for it. If in doubt, run the code. Now the reason this might take a little while to run is because if you remember, when we batchified our data set up here, we've got this map function, getImageLabel, which is going to process our images. So that's why when we're working with batches now, because whenever we run it, it's going to process our images in the background. So there we go. So instead of dealing with file names now, we're actually dealing with processed images, so a little bit more data. This is a massive array, right? Because we've got train images. This should be, let's see how long it is. Can you guess how long if it's in a batch, if it's a single item in a batch? And how long is train labels? Should have really run that in the next cell so it didn't have to batchify our data. 32. There we go. So this is where next comes in. So we've taken our train data, unbatched it using as numpy iterator, or turned it into an iterator. We've taken the next, so the one off the top, so essentially just taken the batch off the top, and returned the images and the labels. Whatever batch you're working with, we're working with images, so this is why this is train images. If you're working with some other type of data, this would be that other type of data, and this would probably still be your labels. But they are of length 32 because our batch size is 32. So now let's use our code, our visualization function. Now let's visualize the data in a training batch. What did we call it? Show 25 images. Show 25 images. Train images. Train labels. Wonderful. So this is the data we're working with. This is our training data. Notice how they're all squares because we've resized them 224 and 224. And this is why I wanted to plot the axis off, because we want to get rid of that junk around the side. So let's do that because we're trying to display images here. Let's plot it again. Awesome. This is our training batch. Now if we come up here, let's do the same for visualizing a validation batch. If we run this again, Oh, actually, I want to show you something that's going to highlight the difference. If we copy this down here, we can remove that as well. This is what I was looking for. Every time we run this, so take note of this one here, Saluki, Tibetan Terrier. Just remember these 5 images here. Now let's try run this again. We see how the top row is different, and you'd notice the rest would actually be different as well. Now, why do you think that is? It's because if we come up here, when we create a training batch, every time we call the training batch, it's going to shuffle the data. So if we were to go do this again, while that's running, we'll write out one for the validation set. Now let's visualize our validation set. So we'll go val images, val labels equals next, val data dot as numpy iterator. Wonderful. And then we'll go show 25 images, and we'll go val images, val labels. So we'll run that, and we notice that we've got some different ones here. Hey, look at that. That dude's holding that puppy. I could do this all day. Just look at that thing. How cute is that puppy? So we'll run this one more time. Take note of this one. Remember this guy holding his dog here. Remember this one that looks kind of like a shower curtain. So we'll run that training. And notice this for validation as well. So remember this dog in the bathtub and this one under the chair. We see the train images have changed, because if we go back up, when we created our data batch, we shuffled the training images every time we create a batch. And for our validation, this one in the bathtub's still here, because we come up to where we created our validation batch. We don't shuffle the validation data. Now, keep thinking about why that might be important. We'll get to that in a moment. I know I've said that a few times now, but just want to have you think about it for the time being. And so, now that we've visualized, we've created data batches, and now we've visualized them to make a bit more sense in our head, I think the only next step is to see what we can do about building and training a model. Let's get on to that in the next video. Now that we've got our data in the form of tensors, more specifically batches of images in the form of tensors and labels in the form of tensors, we can go back to our little workflow. Let's clean up our notebook a little bit, and we can visualize what's happening with our data batches. Let's go check out our workflow. Boom. We've done step 1, get data ready, turning into tensors. And now this has taken a fairly long time to get to, but this is what I want you to remember, is that if we go here, what are we focused on? A lot of our time is spent lining up our inputs with our outputs to make sure that they're consistent with a machine learning algorithm. So we want to input something, in our case, our photos of dogs with their labels in the form of tensors, into a machine learning algorithm. And then we want it to output some sort of learned patterns so that we can make predictions on more images over here. Fit the model to the data, make prediction, and then evaluate them and improve and save our model later on. So this is where we're up to now. Picking a model from TensorFlow Hub to suit our problem, aka our machine learning algorithm that is already implemented. Let's create a little section for doing that. Let's go. This is called building a model. There's a few things we need to define, and that is what we've just seen here. The input shape of our images in the form of tensors to our model. We need the output shape, aka the image labels in the form of tensors of our model. And the URL of the model we want to use. And you might be wondering, URL, that's interesting. Well, this is where we're going to find out what TensorFlow Hub is. So let's write this down, what we need. We go, before we build a model. Now, I want to also stress that in machine learning and deep learning and TensorFlow in particular, there is 1,000 ways to skin a cat, pun the pun. We're using dogs as our classifying problem. This is only one way of how you can build a deep learning model. And we're going to utilize transfer learning. So rather than building a model from scratch, we're going to take what an existing model has already learned and apply it to our problem, which saves us on energy in terms of training a model could take a long time, cost because training a machine learning model isn't free. And then once we've found some baseline results, we can try and improve them from there. So before we build a model, there are a few things we need to define. One is the input shape, our image's shape in the form of tensors to our model, and the output shape, image labels in the form of tensors of our model, the URL of the model we want to use. And we'll turn this into Markdown. Wonderful. These three things, maybe not the URL. You might build a model from scratch, but we're using a URL so that we can get started experimenting as quick as possible. These three things will be standard practice with almost whatever machine learning model you use. Defining the inputs, defining the outputs, and defining the model. And because we're using TensorFlow, everything will be in the form of tensors. Set up input shape to the model. And now I'm going to define this as what it is, and then we'll figure out where these come from in a second. But I want you to have a think about what this might be. So where have we seen none, image size 3 before? If we go here, remember what image size is? 224. So if we come up, remember how we checked the shape of our data batch? None, 224, 224, 3. Well, that is the input shape of our image. And we've got batch, height, width, color channels. Wonderful. And now we want to set up the output shape of our model. If we want our model to predict labels, what might our output shape be? How many different labels do we have? So let's go len unique breeds 120. So we could just put that as 120, but what we might do is just write this in code. So that's the output shape of our model. So we want it to input an image, find some patterns in that image, and then if we fed it an image in the future, one it hasn't seen before, we'd like it to find patterns in that image, and then output, after it's learned some patterns, output an array of length unique labels, which hopefully contains the correct label of what dog breed is in that image. And now here's where we're going to go set up model URL from TensorFlow hub. Equals. What might this be? I want you, before we get to the next video, I'm going to go through it in the next video, is to go through TensorFlow hub and just have a play around, just have an explore and see if you can think about the problem that we're working on. We're doing multi-class image classification. Think about that and see what you can find knowing that by just Googling TensorFlow hub and knowing our problem domain. What information can you find out from TensorFlow hub? Because that's exactly what we're going to be doing in the next video. So have a try yourself and I'll see you soon. Welcome back. Now, hopefully you've had a chance to check out TensorFlow hub. If not, that's okay. That's exactly what we're going to check out now. So let's go here, TensorFlow hub. We'll search that up. Boom, TensorFlow hub. Let's read about it. So TensorFlow hub is a library for reusable machine learning models. Okay. So TensorFlow hub is a library for the publication, discovery, and a consumption of reusable parts of machine learning models. Beautiful. is a self-contained piece of TensorFlow graph along with its weights and assets, aka patterns, so the patterns a previous model has learned, that can be reused across different tasks in a process known as transfer learning. So transfer learning can train a model with a smaller data set, wonderful, improve generalization, and speed up training. That is what we are interested in. Look how quickly you can get started by using a TensorFlow model. How beautiful is that? And so this is TensorFlow Hub. And now TensorFlow is one of the biggest deep learning frameworks that's out there, and it's the one that we're using right now. But I want to also show you, there's also PyTorch Hub and Model Zoo and papers with code. Don't worry, I'll link all of these. So Model Zoo, deep learning code and pre-trained models, PyTorch if you're using PyTorch. So let's just let all these load. Unlike scikit-learn, if you remember, we have the scikit-learn machine learning map. If we go here. So unlike scikit-learn, which has been pretty established for a fairly long time using more traditional machine learning techniques, we've seen this map before in the scikit-learn section. One of these is kind of yet to be created for deep learning and neural networks. And remember, neural network is just another type of machine learning module. And so this is why we have these type of resources like PyTorch Hub, TensorFlow Hub, Model Zoo, open source deep learning code and pre-trained models, papers with code. Papers with code is like the latest trending research of the deep learning field, and oftentimes you'll have the paper, so an academic paper, and the code to go along with it on GitHub, which is absolutely amazing. And so these are some of the resources you should be coming to when you're first getting started. Exactly like what we're doing in Dog Vision, where we're going to find out how to choose a URL in a second. But because the book on deep learning and machine learning is still being written, learning to build things from scratch when you first start is a great approach, but instead, the approach we're taking is focusing on working on a project first, and then if you wanted to dive deeper to get anything like that's going on behind the scenes of what we're doing, you can do that. So don't let me control your zoom level as how far we're going in terms of depth. Once you start to solve problems, like we're doing with Dog Vision, working end to end, you won't be able to help yourself. You'll be compelled. You'll want to dive deeper and figure out how to improve what we're working on. That's the best thing that I can kind of impart on you, is rather than showing you how to do every single thing, which would take a whole documentation, a course that's 4 times as long as this one, and a lot more, it's better to just spark an interest, and then on your own self-search and self-discovery, you find resources like these and try and implement them on your own problems. So that's what we're focused on in Dog Vision, is building an end-to-end project, and then you can take what you've learned in Dog Vision, go to these resources here, Model Zoo, papers with code, and try and apply what you've learned to your own project. And then once you get that little taste of working end-to-end on a project, you'll really start to want to go, hey, I need to figure out what's going on behind the scenes then, and then your knowledge will just grow from within itself, which is a beautiful thing. So that's a kind of long-winded philosophical speech on our training philosophy here. Let's see what we can do with TensorFlow Hub. So hello and welcome to TensorFlow Hub. Beautiful. So there's a bunch of tutorials about how TensorFlow works, but you can browse by problem domain. This is what I was talking about. This is why it's so important to be able to define your problem, like way back up in the top of our notebook. What's our problem? Identify the breed of a dog given an image of a dog. Okay, nice and simple. Then this is a beautiful thing about Colab, right? You can just jump back and forth between your notebook. So let's go to TensorFlow Hub, image. Beautiful. And what do we see here? Well, this could look like a whole bunch of jargon. What's happening here? But let's pay attention to what's going on the left. We got image augmentation. Is any of these tags our problem? Augmentation, no. Classification, yes. Image feature vector, generator, detection, image others, RNN agent. Let's just look at image classification problems. All right. And so what's going on here? Well, this is kind of like the TensorFlow version of the scikit-learn machine learning map. Again, this is still in development phase. So just a couple of years ago, this thing didn't even exist. So this is how beautiful the field is getting now. We're starting to go, okay, these are all machine learning models. I just gave that away, that spoiler. And these are ones that work pretty good. So rather than retrain a machine learning model from scratch every time and take up a bunch of computing power and a bunch of time and a bunch of resources, let's just publish all the patterns that we find in previously built machine learning models so that other people can apply them to their own problem. What could we find? Let's have a look at architecture. Architecture is another word for machine learning model or neural network architecture. With neural networks, you'll probably find that they have some pretty fancy names like Inception ResNet v2. Sounds like a crazy movie. ResNet v150, ResNet v250. And now I want to show you something about ResNet. We're actually not going to use this one, but I want to just show you the power of what it's like. So if we click on here, this is going to give us a link copied to clipboard. That's as easy as it is using a pre-trained ResNet model. We can copy that URL, or we could download the model. But if we go here, this is how we create a ResNet model. The reason why I want to show you ResNet, especially ResNet 50, is that Tesla use ResNet 50 backbones. This is why transfer learning is so important to understand, is because if we go here, this is ResNet v250. I took this slide here from a talk called PyTorch at Tesla by Andre Karpathy. You can watch it there, I'll be sure to link it. But their computer vision systems in their Tesla cars use ResNet 50-like diluted backbones. Of course, they'll have custom layers and whatnot. But what I'm saying is that we have access to very similar machine learning models as what are being used in production at companies like Tesla. So that's why it's important to be aware of these resources that are available to us. And I know that this says PyTorch, but the beautiful thing is if you come up to PyTorch Hub, you could probably find it. There you go, ResNet 101, all that sort of stuff. Now, we're working with TensorFlow. Let's go back to here. I have a model in mind that we want to use. So we go architecture. This is going to take a little bit of exploring on your behalf, but what you can essentially assume here is that the higher the number, the better the model. But also the trade-off there is the higher the number, the longer it takes to train. So MobileNet, this is your homework for this video, is to Google MobileNet. Just look it up and just read about it. So we're going to use this one here, image classification. So if we have a read about this, TF2 save model, this is a save model in TensorFlow 2 format. It requires using TensorFlow 2 or 1.15 and higher. So that's what we're using, TensorFlow 2, beautiful. So MobileNet v2 is a family of neural network architectures for efficient on-device image classification and related tasks, originally published by, so that's where it was originally published. Now, remember right back at the start what our problem is? I was sitting at the cafe the other day. This beautiful dog came walking past and the friend I was with said that's an Australian Terrier. And I was like, wow, I wish I could take a photo of that dog on my phone and figure out what kind of dog it was. So this is where we come to MobileNet. Wow. It's efficient on-device image classification. That's exactly what I want to do with dog vision. Beautiful. So we can come here and we can see it's got some guidelines of what we can do. This is your homework as well, is to read through this. Even if you don't understand it at first go, just have a read through it. And we'll leave this link in the resources section. By the way, this is where we got that batch input shape. There we go. 224, 2243. Little number on the end here. But if you were reading through this, that's where you would figure that out. So let's copy this to the clipboard. Come back, and this is our model URL. We're going to change that into a string. And we're going to put in here from TensorFlow Hub. And then we'll put a link to TensorFlow Hub. Wonderful. Come back to dog vision. There we go. So what have we got set up now? So if we come back to our keynote, this is what we've set up. We've picked a model from TensorFlow Hub to suit our problem. Remember, we went through our problem domain and we're working with images. What we're focused on is our inputs. We've done that. We've got our data ready. We turned it into tensors. And we've chosen our machine learning algorithm. Wonderful. And now we've got our output shape correct. Now we've got these three key criteria. We have to work out how we can use them all together. The next process is putting them together in the form of a function that's going to create a model for us and return it so that we can fit it to our data set. So let's get started on that in the next video. But remember, for now, your homework is to read up about TensorFlow Hub and to check out MobileNet v2 130.224. I'll link both of these and these other resources in the resources section. Now we've got the inputs, outputs, and model we're going to use ready to go. We can start to put them together. And one of the ways that we're going to do that is, well, one of the things to remember is there's many ways of building a model in TensorFlow. But one of the best ways to get started is to use the TensorFlow Keras API, which is a recent addition to TensorFlow 2.0. So if we go TensorFlow Keras, we just Google that. There we go, Keras, TensorFlow Core. Here we go. TF Keras is TensorFlow's high-level API for building and training deep learning models. That is what we're after. It's used for fast prototyping, state-of-the-art research, and production with three key advantages. User-friendly, yes. Modular and composable, yes. Easy to extend. This will probably be a good resource to link. I'll link this in the resources section. It's another little bit of homework for yourself, is to just have a read through this after this video, maybe go through it for about 10 minutes or so. The question I want to ask, and leave a message in the Discord or the Q&A, is what is the difference between Keras sequential and where is functional? And functional. So that's what I want to know. The difference between the Keras sequential API and the functional API. As a spoiler, we're going to be using the sequential. So go through the Keras TensorFlow guide, Keras overview for 10 minutes. And the question you got to answer, the difference between sequential and functional API. But let's not waste any time there. Let's get hands-on with the code. And the beautiful thing about Keras is that defining a deep learning model can be as straightforward as saying, hey, here's the layers of the model, aka, let me go back to this little graphic. When I say layers, often in a neural network, these are what are referred to as layers. So you'll have an input layer, which will be here, aka this one. Then you'll have some sort of other layer here, which is often referred to as a hidden layer, which is going to find some patterns, and then an output layer. So that's what I mean by layers. And so in Keras, it's kind of as easy as going, hey, here are the layers of the model, the input shape, the output shape. Let's go. So let's create a function that does that. So what we might do is write out. We'll make a little markdown cell, change this into markdown. Now we've got our inputs, outputs, and model ready to go. Let's put them together into a Keras deep learning model. Wonderful. Now, remember how right at the start we said we want to start getting functional about what we're doing? So we could write out the code line by line, but we're going to put it into a function. So we go, knowing this, let's create a function which, if we go here, takes the input shape, output shape, and the model we've chosen as input, or as parameters, that's probably a better word to say. And we go defines the layers in a Keras model in a sequential fashion, aka do this first, then this, then that. So it's just like a linear step-by-step process. Here's the inputs, here's the middle layer, here's the output layer. So just running sequentially from left to right, or in deep learning, you often run like from top to bottom. We'll see that in a moment. And then we go here, compiles the model, says how it should be evaluated and improved. We haven't seen that one before. That's a new term. Don't worry, we're going to go through it. And then we want to builds the model, tells the model the kind, or the input shape, that's better, the input shape it'll be getting. And then finally returns the model. That's a fair few steps in there, but we can do it. And if you're wondering where I got this one from, builds the model, we can come up here into, oh, we closed it. So tf hub.dev. If we go here, back to MobileNet v2, this is that step there, m.build. But we'll see this in a moment. And if you're wondering where any of these other steps are, you could pause this video and have a read through this. Even if it doesn't make sense, don't worry, because we're going to code it up in a second. Have a read through this and then come back here. If not, if you don't want to read through that, we'll just keep going with the code here. We'll go here. All of these steps can be found here. This is just a way of documenting for our own sake. All right, so let's write the code first, and then we'll discuss each part. I think that's a better way to go. So create a function which builds a Keras model. So def create model. This is our own custom function. This is what we want to get used to writing. So it's going to take input shape, which is just there. Wonderful. Output shape equals output shape. And then it's going to take model URL. This is handy because if we wanted to change the model we were using, we could just update the model URL variable. And if we wanted to similarly change the input shape and the output shape, we could also change those later on. So print, we just want to find out what model we're using. So let's go building model with just the model URL here. And now we're going to set up the model layers. So model equals tf.keras.sequential. And then we want to write hub.keras layer. And we're going to pass it model URL. So this is layer 1, the input layer. And then after that, we want to do tf keras.layers.dense, and then the number of units equals our output shape. And the activation, which is a word you probably haven't heard before, equals softmax. Layer 2, this is the output layer. Now, just bear with me. If you don't understand it, that's all right. We're going to go through it. This is just practicing writing the code. I'd like that to be over here, actually. I have a strange feeling Colab uses 2 spaces instead of 4 spaces, but we'll find out in a moment. There we go. That looks a bit better. So without even discussing what's going on there, I want you to just have, oh, actually, that looks a bit better if it's over here. That's a bit more Pythonic. I just want you to have a think about what's happening here. And if you wanted to help your thought process, don't forget, you can always read through here. So now we want to compile the model. Again, a term we haven't heard, but we're going to discuss these shortly. So compile, we just want to get used to writing this sort of code. So this is just instantiating a model. And this is putting the model together, essentially. So Keras.losses.categorical cross entropy. Wow, that's a big word. It's all right if it's confusing. tf.keras, the optimizer. What is an optimizer? .atom. Atom. And then metrics. This one will be familiar for sure because we're working with classification. Accuracy. Whew. And then finally, you want to build the model. So model.build input shape. And then we're going to return model. So now, let's run the code. If in doubt, run the code. So model equals create model. We can use all of the default parameters. And then we're going to go model.summary. Building model. Shows us our URL. Oh, what have we missed here? No attribute optimizer. Optimizers. There we go. What else have we got wrong? Oh! What is this? We haven't seen this before. In fact, a lot of this we haven't seen before. But we're going to end this video on a little bit of a cliffhanger, because in the next one we're going to go through this and discuss it. But in the meantime, I'd like you to rewrite this at a bare minimum for yourself and to have a think about what's going on here. Also check out this. What do you think we've done here? And after you've written the code and after you've gotten this output, read a little bit through here, especially the sequential model section, and see if you can relate it back to what we're doing here. But otherwise, I'll see you in the next video and we'll go through what's happening here. Now we've got a beautiful function to create a model for us, and we've actually used it already. We've instantiated a model and got the summary. You might be looking at this like what's going on here, even looking at this like what's going on here. So let's go through this step by step and figure out what's actually happening. So first of all, we instantiate a model. So set up the model layers by using model equals tf.keras.sequential. What's happening here? A linear stack of layers. So when it says that, what it actually means is it's just a stack of layers that's going to take some sort of input, find patterns in that input, and then have some sort of output. That's what the linear stack of layers means. So if we look here, what's the first layer? It's going to run from top to bottom. And here we go. Here's another Colab error. You might see this. Hopefully it fixes itself. Otherwise, we can fix that later. The first layer is hub.keras layer model URL. What this is saying is it's telling TensorFlow Hub to create a Keras layer. So what we're doing is we're using Keras to build our deep learning model. It's telling it to create a Keras layer of model URL, which is our MobileNet v2 architecture. So you might be wondering, what's going on with MobileNet v2? And why do we only have 2 layers? Well, let's check that out. Let's go MobileNet v2 architecture. So here we go. Review, MobileNet v2, lightweight model image classification. So this is what I do when I'm trying to figure out what's going on with a model that I'm using. Maybe I've found a model from TensorFlow Hub, or maybe I've seen a tutorial or using some sort of model. I'm trying to figure out what's happening. So we got MobileNet v2 convolutional blocks. Now, if you wanted to check out that, you might want to look up, this is conv is short for convolution. So you might want to go, what is convolution neural network? So I'll leave a great resource for you to check that out, but here's essentially what's happening. That's a good image, actually. Oh, another Medium article, beautiful. So here's what's happening. We have an input image, and then MobileNet v2 has a whole bunch of these type of layers built into it. So they're going to look at the input image, do some data transformations on it, and then output it to something, aka a list of numbers. So this is what our job is. If we come back to the keynote, we've prepared our inputs and we're passing it to the machine learning algorithm, in our case MobileNet v2, and it's going to output something. So the beautiful thing about transfer learning is that all of these parts are taken care of for us using MobileNet v2. We've defined our inputs, and this is what we want at the end, some sort of output. Now let's come back to this review of MobileNet v2. And it's okay if you don't fully understand about what's going on here. This is part of the experimentation of deep learning and machine learning. It's figuring out what's going on, what is happening to our data when we transform it. Our first focus is to always write working code and then figure out what's happening after that. If we want to dive deeper, we can. So the overall architecture of MobileNet v2, it takes an input of size 224 squared times 3, aka the height and width of our images times color channels. It does a whole bunch of transformations. So takes this input, does transformations like this. Okay, and then finally it's going to output a single list of numbers that are a size of 1280. So that's the last layer. And now you'll see this overall architecture in papers and whatnot. Hopefully, if they're a good paper, they've included this. And if they're an even better paper, they've included code. And you'll see this and you'll be wondering, what is this? Well, it's something like this. Again, you'll be wondering, what is this? So let's have a look what it might look like in NumPy. So if we go outputs equals NP, let's just do ones of shape equals 1, 1, 1280. And then outputs. So it's just going to be a long list of different numbers. But 1280, we don't actually need that, right? This is where our dense layer comes in. This is where our outputs come in. We want our outputs in the form or in the shape of 120 because that's how many labels we have. So let's put this all together. We have an input of an image. MobileNet v2 is going to go through for us and find all the patterns and then condense them into one long array of numbers, 1280 long. But then this is the beautiful thing about transfer learning is because all of this has been implemented for us, all we have to do is say, hey, actually, instead of that 1280, we want our output to be in the shape of however many labels we have. And you might be wondering now, okay, what does dense do? Let's look at the docstring. Just your regularly densely connected NN layer. Well, thanks docstring, that actually doesn't make too much sense. But you might be wondering what the activation is. Now, softmax, let's check that out. What is softmax? And this is where you're going to get a whole bunch of mathematical jargon. But let's just go to Wikipedia. Now, if you read that first line, it might sound pretty confusing to you, unless you've got a mathematics degree or something like that. But the main thing here is that after applying softmax, each component will be the interval 0, 1. And the components will add up to 1. Now, we will see this later on, but that's all you have to know for now. And if you're wondering, what softmax do I use? Which activation, which loss function? If we're working with binary classification, the activation function is sigmoid. So we come here, sigmoid. And if we're working with multi-class classification, the activation is softmax. Softmax. So that is what is happening in here. We're creating a Keras model. It's going to run in sequential fashion. The first layer it's going to call is the model URL, which is actually the MobileNet v2 architecture, which has been implemented for us. And within that MobileNet v2 architecture is going to be a series of convolutions, which are going to find patterns in our input images and learn the features of those images. If you're wondering what a feature is, let's come up to an image. Let's take this one, for example. A convolution may look at each pixel in this image and go, okay, there's a vertical line, There's a circle here, there's a circle here, there's a horizontal line here. Now, the thing is, we don't tell the model which of these features it learns. It figures them out on its own. So that's the important takeaway there. That's the whole premise of machine learning, is that it figures out the patterns in these images for us. So we come back. So once it's gone through the MobileNet v2 architecture, it's going to output a single array of size 1280 with all of the patterns it's learned in an image. But we want to tell, hey, we want to go, no, we don't need 1280 patterns. We need 120. And then we want to use the activation softmax to convert those patterns into numbers between 0 and 1. And then the highest number, so all of the outputs, so it'll be an array of 120, all of those will add up to 1, and the highest value is which one is our label. Now that was a lot to take in, but we're gonna, over the next few videos, break this down even more. So in the next one, we're gonna go through what's happening when we compile a model. So I'll see you there. In the last video, we broke down what's going on here. What we're doing is essentially just passing Keras' sequential model, an input, aka our image of a dog, and then MobileNet v2, aka this model URL that we're using, is going to find the patterns inside it. And then we're going, hey, no, we don't want the same shape as MobileNet v2. We'd rather convert it to the size of our own output shape, which is the amount of labels that we have, or the amount of unique labels that we have. So now let's talk about what's going on in compile. Oh, and by the way, if you do want to dive deeper on any of this, I encourage you to search it up and figure it out and try out yourself. We're going to see the outputs of this later on, so we're going to actually see the code running. But whenever you look up something and try to figure it out, even if you don't understand it the first time, trying to figure things out for yourself is a way to really cement your knowledge. So if anything here you want to look up and find more, don't be afraid to ask a question, and don't be afraid to look it up and check it out, what's going on behind the scenes for yourself. Now, what is happening with model.compile? This is something else you'll see when we're building a model with Keras. And so I think this one is best explained with a story. Let's say you're at the International Hill Descending Championships. That's right. You're one of the world's best at going down hills. And you start standing on the top of a hill. And now your goal is to get to the bottom of the hill. But the catch is that you're blindfolded. And luckily, your friend Adam is standing at the bottom of the hill shouting instructions at you on how to get down. And at the bottom of the hill, there's a judge evaluating how well you're doing. They know where you need to end up, so they compare how you're doing to where you're supposed to be. And their comparison is how you get scored, aka your accuracy at getting down the hill. You might be wondering, Daniel, why am I at the International Hill Descending Championships? Well, let me break it down. This is where the model.compile comes into play. Let's turn it into this terminology, because this can seem very confusing when you first begin. So the loss. So the loss is the height of the hill. Now, our model's goal is to minimize the loss, getting it to 0, aka getting to the bottom of the hill. So this means that the model is learning perfectly. Loss is a measure of when the model is learning, so when it's going through the training set and comparing the image to a label. The loss is a measure of how well the model is guessing. So when it's trying to make a prediction whilst it's learning, the higher the loss, the worse the prediction is. So the worse the model is learning patterns. The lower the loss, the better the model is learning patterns. Just like you, if you're descending the hill, the higher you are on the hill at the International Hill Descending Championships, the higher you are, the worse off you're doing. So your goal is to get to the bottom of the hill. And now if we come back, let's discuss what the optimizer is in our hill story. So your friend Adam at the bottom of the hill who's telling you how to get down the hill is the optimizer. He's the one telling you how to navigate the hill aka lower the loss function, so how high you are on the hill, because he can see what's going on. He can see your movements. So he's basing his instructions on what you've done so far. And now his name is Adam, your friend's name is Adam, because the Adam optimizer, yes, it's actually called the Adam optimizer, is a great general optimizer which performs well on most models. So if we have a look at this, we go Adam optimizer. Adam, the latest trends in deep learning, gentle introduction for Adam optimization. And if we go machine learning model optimizers, it's going to tell us a few more types of optimization algorithms. So this is what's going on here. The loss function is how high you are on the hill. You're trying to minimize that because you're at the International Hill Descent Championships. The optimizer is your friend Adam at the bottom. You could also use another optimizer called RMS prop or stochastic gradient descent. But generally, to begin with, Adam is pretty good on most problems. So Adam's telling you how to get down the hill because remember, you're blindfolded. You're a model who's going through the training data for the first time and trying to learn patterns, or trying to go down the bottom of the hill for the first time blindfolded. And then finally, the metrics here, this is the onlooker at the bottom of the hill. This is the judge of how well your performance is at the bottom of the hill, telling you how you're going at the championship. So in our case, it's giving us the accuracy of how well our model is predicting the correct image label. Whew. So that's a fair bit to go through, but these are 3 parts of most deep learning models. Basically all of them. You're going to have some sort of loss function, so how well your model is guessing. You're going to have an optimizer function, so a function that helps your model improve its guesses. And then a metric, which is a way of evaluating those guesses after it's learned. So this is a step that we're going to have to take with when we're building any Keras deep learning model. We define the model as some sort of layers, and then we define how the model is going to learn. So hold on to that little story. If you have any questions about the story, or if you want to figure out what loss function you want to use, search up something like, what loss function should I use? How to choose loss functions when training deep learning models. Beautiful. This is a great resource, or it might be. I'll leave a resource there, how you can choose a loss function. But mostly it's going to depend on what problem you're dealing with. So if you're using binary classification, aka if you're predicting whether something is one thing or another, such as images of cats or dogs, you would want to change your activation function to sigmoid, and then your loss function to binary cross entropy. So we change this to binary cross entropy. But because we're doing multi-class, we keep it at categorical cross entropy. Because if we come here, multi-class classification, activation softmax, loss, categorical cross entropy. Now this is a lot to take on. So don't worry if you don't get it to begin with, but remember the hill story. Remember what the loss is. Remember what the optimizer is, just your friend Adam telling you how to walk down the hill. And the metrics, you could use a bunch of different metrics here. So if we go here, TF Keras metrics. This is going to tell you some metrics that you can use. Accuracy is the default one for classification. But we've got area under the curve, categorical accuracy, a whole bunch. Mean, precision, recall. So a whole bunch of different options. I'll be sure to link those as well. But that, we've gone through what compiling the model does. And then finally, we can finish off with this one, because building, I think you can imagine what's happening here is just another little way to say, hey, this is the input shape we're going to take to our model. So we're using a Keras layer from TensorFlow Hub. And if we come back to here, it says that if we want to use this layer, we set up a sequential model and then build the model with our input shape. And it's this shape because that is the size of images that MobileNet v2 was trained on. All right, now that has been enough talking. We've broken down what our create model function does. If you have any questions, be sure to leave it in the question and answer or in the Discord chat. But let's have a look at what's going on. We'll probably actually in the next video just quickly debrief what's going on in summary. But the next thing we want to do is create some callbacks for our model. So while our model is training, callbacks are going to be some functions that are going to implement a few little helpful things that our model can do while it's learning patterns in the data. So I'll see you in the next video. All right, and now we've got this fancy function, create model. What's happening here when we call model.summary after we've created an instance of our model? We've got layer type, Keras layer, so we go up here. We've got, okay, hub Keras layer, that makes sense. We've got output shape multiple and param number 5,432,713. That's a fairly large number. We come here, total parameters. Then we have down here trainable params and non-trainable params. And it seems that the non-trainable params line up with this param number or parameter. Params is short for parameters. And we have another layer here called dense with param number 120,240. That corresponds to our dense layer here. Well, this is one of the amazing things and the benefits of transfer learning. The reason it says non-trainable params or parameters is because we're using MobileNet v2. And now if we come up here, these are the patterns that MobileNet v2 has learned throughout these layers here. Or by repeatedly going through, if we come back up to the top of this article, by repeatedly going through our images, or the images that MobileNet v2 was originally trained on, better, that's the correct terminology there. So it's gone through all of these images, and if you're wondering, what images did MobileNet v2 go through? Well, it trained on, if we read through here, if we go ImageNet. There we go. So its weights were originally obtained by training on the ILSVRC 2012 CLS dataset for image classification, ImageNet. Okay, let's look up that. ImageNet. ImageNet. ImageNet is an image database organized according to the WordNet hierarchy. Okay. Currently we have an average of over 500 images per node. Okay. So essentially ImageNet is a large database of over 14 million images. And so that these patterns, these parameters, are what MobileNet has learned by training on ImageNet. And so this is the beautiful thing about transfer learning, is that all these patterns that MobileNet has learned through these layers here, and by the way, this is why they call it deep learning, because essentially each one of these layers is a layer in our neural network. So if you imagine this, expand it out, each one of them is a layer, and hence the reason they call it deep is because the diagrams are usually, they have an input layer and then it just keeps going down and down and down and down and down. And so inherently, what each of these layers actually are is a small model within themselves. So these are just multiple pattern finding models layered on top of each other, hence the term deep learning. So if we come back, this is what our base layer is. Those 5.5 million patterns that MobileNet v2 has found within ImageNet. And now we get to utilize those patterns that it's found in our own problem. So rather than try and find them from scratch on our own, which could take hours and lots of compute power that we don't really have, we get to utilize them and train our own 120,000 parameters. So this is our dense layer here. That's what we're going to be training. So we're going to be passing our images to MobileNet. It's going to be using its baseline patterns to figure out what's in our images. And then finally, we're going to stick this layer on top and go, hey, we've got our own data that isn't in ImageNet. But let's use what you figured out in ImageNet for classifying which dog breed is in a certain photo. Now that we have a model, we probably need to make some callbacks. And you might be wondering, what are callbacks? Well, let's save that for the next video, where we'll create some callbacks. And then after that, we'll create a function that's going to train our model. That sounds like a good idea to me. We've got a model up here ready to go, and we've checked out what summarizing it means. But what we'll do first is create some callbacks. So let's make a little heading here, and you might be wondering, well, what are callbacks? And that's what we're going to dive into in this lesson. And we'll write down here, callbacks are helper functions a model can use during training to do such things as save its progress, check its progress, or stop training early if a model stops improving. And plus there's a few more. These are just a few things, and these are the ones that we're going to implement. Now, you might be wondering, why should we implement callback? If you want to find out a bit more about model callbacks, we can go TensorFlow, Keras, model callbacks. And this is going to bring up the documentation. Keras custom callbacks. Excellent. So there's a few more callbacks that we can do in there. Oh, there's one, TensorBoard. We're going to be setting that up. And so while a model's training, because it can be training for a long time, you might want to figure out what it's actually doing. So there are times where once you scale up your models, our model won't take this long, but you could be training a model for up to a week at a time, especially some of the biggest deep learning models. And so if your model is training for a week, you're probably going to want to know, how's it going, what's it doing, and if it's training for too long, yes, that's a thing, you probably want to stop it early before it begins to overfit. But we're getting ahead of ourselves here. Let's create a couple of callbacks so we can see it in action. That's going to help solidify what's going on. Same with what's going on up here. This function's a fair bit to take in, but once we start to use it, once we start to train a model, you'll start to see what's happening. Now, what two callbacks do we want to make? We'll create two callbacks. One for TensorBoard, which helps track our model's progress, and another for early stopping, which prevents our model from training for too long. Now, these are a couple of handy callbacks that you can create with basically any model. It's just TensorBoard, which is like a dashboard for seeing how well your model's doing, seeing its progress, seeing that the loss function is getting reduced and that the accuracy is going up. They're the two main ones we'll be looking for. An early stopping callback is something that if our model is training for too long and it's stopped improving, before it overfits, we want it to stop training. So let's go here. We'll go TensorFlow callback. Oh, no, we want TensorBoard. TensorBoard. So let's see. We might actually go in here, callbacks, TensorBoard, and see what it says. There we go. There's the documentation for the TensorBoard callback. But let's code it up first. So to load TensorBoard into the notebook, you can go load. There's a magic function, TensorBoard notebook extension. We go load extend TensorBoard. Wonderful. So that's going to load the TensorBoard extension into our notebook so we can have a look at TensorBoard inside here, inside the Colab notebook. And now we're going to see this in a moment, so just bear with me. To set up a TensorBoard callback, we need to do three things. Maybe four, that was number one. So let's write that here. To set up a TensorBoard callback, we need to do three things. Actually, it's three things. That was the first one. Number one, if I could type, this would be amazing. Load the TensorBoard notebook extension. We're going to put a little green check mark there. And then number 2 is create a TensorBoard callback, which is able to save logs to a directory. So basically these logs are how our model is doing during training, and pass it to our model's fit function. Now we haven't seen the fit function just yet, but it's very similar to the one you've seen before in scikit-learn. And we go here, visualize our model's training logs with TensorBoard magic function. We'll do this after model training. Wonderful. So let's now create a function. We'll do step 2 here. So the first thing we have to do is import datetime, because our TensorBoard callback, we want to be able to track each experiment. And one of the best ways to track an experiment is by the time that you ran that experiment. So that's why we need datetime to access the current date and time. You'll see this in a minute. So we'll go here, create a function to build a TensorBoard callback. Make it nice and simple. Create TensorBoard callback. And then here, what we're going to do is create a log directory for storing TensorBoard logs. So what we might set up is just a logs file in our dog vision project. I want dog vision, yes, and new folder. I'm going to call this logs. So this is where we're going to store all of the logs for our TensorBoard callback. So we'll X out of that. And now we'll go logdir, create a variable os path join. So this is short for, it's just accessing path names. We need to have access to the path of this logs file. So that's what we're doing here. And we'll create drive / my drive / dog vision / logs. And then we're going to join it with, so make it so the logs get tracked whenever we run an experiment. So every time we fit our model, we want to create some training logs for the current date and time. So this is where we access datetime, .datetime.now, .string. This line here is just saying, hey, get the exact current time. So in my case, it would be Tuesday, 5:25 p.m. And we're going to go string from time. We can do almost any format you want here, but we'll go for a pretty standard one of year, month, day, hour, minute, second. So the log directory, every time we run this function, it's going to create a path in logs with the name appended to it of the current date time. Does that make sense? Well, we'll see it when we run it anyway. And then we want to return tf.keras.callbacks.tensorboard. And we want to pass it logdir. So see here, enable visualizations for TensorBoard. TensorBoard is a visualization tool provided with TensorFlow. Beautiful. So this callback logs events for TensorBoard, including metric summary plots, training graph visualizations. Beautiful, that's what we want. And we need to pass it a logdir, the path of the directory where to save the log files to be passed by TensorFlow. That's exactly what we've created. So, little green tick here, come on. There we go, my emojis. Wonderful. And we'll run that. So we've got our first callback, create TensorBoard callback. Now, in the next video, we're going to create an early stopping callback. And then we might be able to start getting our model ready to train. Oh, actually, we're probably ready to train now. Because we're setting up these experiments that we want to be able to run back to back to back, this is why we're creating callbacks ready to go. So I'll see you in the next video. We'll create an early stopping callback. Alrighty, so we've got a TensorBoard callback, which is going to help us monitor our model's performance as it's training. So figuring out if it's learning correctly, is it doing well or not. Now let's create an early stopping callback. Early stopping helps prevent overfitting, so our model learning the training data too well, by stopping a model when a certain evaluation metric stops improving. So if a model trains for too long, it can actually do so well at finding patterns in a certain data set that it's not able to use those patterns on another data set, so it doesn't generalize well. So if we come back to our exam, if you were to learn the course materials far too well, like you learnt them off by heart, aka if you're in university and you studied way too hard on the course materials, you've memorized them off by heart, when you come to a practice exam or a final exam with questions that you haven't seen before, if you've memorized everything on here, instead of just learning the inherent problem-solving patterns of the course materials, you're not going to do very well on the practice exam or the final exam. So you're not going to be able to generalize very well. And so early stopping helps prevent our model from overfitting the course materials, aka the training set, so that when it comes to a data set that our model hasn't seen before, it's able to perform well. Let's see it in action. We'll create an early stopping callback. We'll go here, like this. Early stopping callback. And we'll change that to Markdown. Wonderful. And so if we go up here, we could go TensorFlow, Keras, early stopping callback, and this should take us to the documentation. There we go, early stopping. So that's what you can check out there. Stop training when a monitored quantity has stopped improving. Let's do that. Might just link this in here, why not? Beautiful. And we'll write a little note here. Early stopping helps stop our model from overfitting by stopping training if a certain evaluation metric stops improving. So to set up early stopping is pretty simple. So we'll go create early stopping callback, and we'll go early stopping equals TF Keras callbacks early stopping. Wonderful. And we want it to monitor, so this is the parameters we pass it to. By default, it monitors the validation loss. So we're going to see this in a second when we run a model, but we might choose validation accuracy. And now you could choose validation loss if you want, but we're going to choose validation accuracy. And we're going to give it a patience value of 3. What is patience? Number of epochs with no improvement after which training will be stopped. What's an epoch? Well, let's figure that out in the next video, I think. So we'll just run this. These are going to make these callbacks as well as this model function are going to make a lot more sense once we start training a model. So that's our early stopping callback ready. We're going to monitor the validation accuracy. As soon as it stops improving for 3 epochs, we're going to stop training our model. So in the next couple of videos, what we might do is I think we are definitely well and truly ready to start training a model. So if we come back to our keynote, what we're focused on, we've picked a model from TensorFlow to suit our TensorFlow hub to suit our problem. We've turned our data into tensors. Now it's time to fit a model to the training data and make a prediction. So how about we make a function for training a model? How exciting is this? Oh, we've gone a long way. From battling to get our images into tensors, our labels into tensors, preparing our data, choosing a model on TensorFlow Hub, creating model callbacks. We're finally at the stage where we're ready to train our first deep learning model. So let's create a heading, training a model. Now we're going to put on a subset of data because if you remember back when we split our data up, we're only going to start training on 1,000 images. Because why do we want to do that? So let's write here, our first model is only going to train on 1000 images to make sure everything is working. So that's what we're trying to do. We're trying to minimize our time between experiments. So we begin by starting on a subset of the data to make sure all of this code, it might break, right? So we want to make sure that it's working before we spend a long time training on 10,000 images. Because training on 1,000 images is going to go a lot faster than 10,000 images. And you could imagine the same goes if you increased it to 100,000 images, or in the case of ImageNet, 14.2 million. So there's one more variable that we have to define before we can get into training a model. And that is number of epochs. And so the number of epochs is how many passes of the data we'd like our model to do. And a pass is, you can imagine, is equivalent to our model trying to find patterns in each dog image and see which patterns relate to each label. Let's go into here, num epochs equals 100, and we're going to do something cool here. We're going to create a little slider like we have before, param, and then we're going to create type slider, and then the min will be 10, the max can be 100, and then the step can be 10. Look at that, how cool is that? So if we wanted to do 10 epochs, we could do 10, but we're going to stick it to 100 because we've got our early stopping callback. And we're going to see all of this in action in a second. But essentially what a training pass is going to do, if we go back to our keynote, one epoch would be giving our model a single chance to look at all of the training data and then validating it from there. 100 epochs, so we're giving our model up to 100 chances to go through the training data set and figure out the patterns. So it's going to, what a pass is, it's going to go through these layers. We're going to pass our training images to our model. It's going to go through these layers. And then our model, as it learns patterns, is going to make guesses on which label belongs to which image. And the worse off the guess is, the higher the loss will be. So that's where Adam comes in. Remember that guy down the bottom of the hill at the International Hill Descent Championships is telling our model how it can improve its guesses with each epoch. And then we're going to see how our model is doing on an accuracy level because we've got that spectator judge at the bottom of the hill watching how well our model is performing. So again, if all this doesn't make sense, it's going to make more sense once we actually start to run a model. So let's do one final check. The final check is one last time to make sure we're using a GPU. Because if we're not using a GPU, this training our model on images is going to take a very, very long time. You saw right at the beginning, a GPU can speed up our code by up to 30 times and sometimes more. Let's write that code. Check to make sure we're still running on a GPU. So print GPU available, and then we're going to go yes if tf.config.list physical devices, and then we want to check GPU, else not available. So this is just the same code we wrote above, but we need a GPU to be able to run this in a considerable amount of time. Yes! We could also have checked here. Remember, that's a little shortcut trick, but I love seeing this print out here. Now, boom, we've got a GPU running, we've got number of epochs set up. Let's create a simple function which trains a model. So let's write that here. Let's create a function which trains a model. And the function is going to create a model using create model. And then we want to go set up a TensorBoard callback using our TensorBoard function. So create, see, this is where creating functions has really come into play for us here. Otherwise, we'd have to be writing code ad hoc, but writing functions to begin with takes a little longer, but in the long run, saves us time. So call the fit function on our model, passing it the training data, validation data, number of epochs to train for, which is num epochs. We just define that with our sick little slider. And the callbacks, which are our helper functions, we'd like to use. And then finally, we want it to return the model. We're going to change this into Markdown. That is looking phenomenal. Okay, let's go here. Build a function to train and return a trained model. So here we are, def train model. I can't believe we're finally up to this. This is amazing. We're training our first deep learning and neural network. So trains a given model and returns the trained version. Nice and simple. Remember, even though we're getting excited, doesn't mean that we're losing our communicative habits. So we'll create a model. So we'll go model equals. See, this is where our create model function comes in. Oh yeah, that's so satisfying to write. And then we go create new TensorBoard session every time we train a model. Because remember, with our TensorBoard callback, we'll just call this TensorBoard. We don't need the callback there. We set up our function. So if we come back up here, every time it's called, it's going to create a new folder in logs with the current date time. So this is important because every time we run our train model function, so every time we try to train a new model, a new experiment, we're creating a logs folder, which we can then track our model's performance. So that's a real helpful thing later on when we're trying to evaluate which experiment did better than another. And then we go fit the model to the data, passing it the callbacks we created. Now again, there's probably a better way to do this function, but we're just trying to make it so that it works, and then we can go back after we've sort of got through the phase of fitting a model for the first time and refine it. So let's go model.fit, and we're going to pass it x equals the train data, which is a data batch, if you remember, which contains the images and labels. So epochs is going to be num epochs, aka how many times is our model allowed to look at the training data before it stops? Or how many chances did our model have to pass over the entire training data set to find patterns? And then the validation data is going to be val data, which is a data bunch as well, or a data batch, sorry. And the validation frequency is how often we want to test the patterns that our model has found on our validation set. And we set it to 1 because we want it to test its patterns that it's found in the training set on the validation data every epoch, so once an epoch. And then our callbacks are TensorBoard, which we've just created above with our function, and early stopping. Whew. And then we want to return model. Put a little return the fitted model. How cool is that? And now we can fit our model to the data by as simple as going model equals train model. You see the benefits in creating functions? So we could run this function after doing a bunch of different experiments later on. And so are you ready? Now, a little tidbit here. When training a model for the first time, especially on image data or any other kind of large-scale data, the first epoch will usually take the longest compared to the rest. Now, this is because the functions that we've written is getting the data and it's been initialized, so aka loading the data into the memory of our GPU. Now, using more data will generally take longer, which is why we've started with 1,000 images. And so after the first epoch, right, we've set it up so that it's capped at 100. The first one might take a couple of minutes. After the first epoch, subsequent epochs should only take a couple of seconds. So you ready? We're going to do this together. Fingers crossed, all of our functions, because this actually depends on a fair few lines of code up here. Let's see if it works. 3, 2, 1. Oh, look at that. Building a model with MobileNet v2. I got my fingers crossed. I hope you do too. Yes! It's starting up. See, there we go. Epoch 1 of 100. Because epochs is set to 100. So it's going to train for 25 steps, which means our batch size. So if we go, we have 800 images in our training set, because remember we started with 1,000. So if we divide that by 32, we get 25. So that's why training is 25 steps, because there's batch size 32. And validation, if we go 200 divided by 32, it's going to round it up. So it's rounded it up to 7. That's why we have validation. So 200 images over a batch size of 32. And check this out. There we go. ETA, about 5 minutes. And so here's what I'm talking about with the loss. So now all these things that we created right up here, so the loss, so our goal is, remember, to minimize the loss. Because we're at the top of the hill, we're afraid of heights. We want to get to the bottom of the hill. You want to minimize the loss function. The loss is the height of the hill. We come down here. So hopefully this number goes down, but we want to maximize accuracy. So that's how we'll know if our model is training or not. If it's learning patterns, this loss should go down and this accuracy should go up. So this is going to take a few minutes to get through the first epoch. I'm going to wait until it's gone through the first epoch, and then, so I'll speed this video up, and then I'll see you once it's past the first epoch, because you're going to see subsequent epochs after this. So epoch 2 out of 100 is going to be pretty quick, because we're using a GPU. The only reason the first one takes a while is because it has to load all of those images into the GPU memory. I'll see you pretty instantaneously, but for me it'll be about 3 minutes. Alrighty, I'm back. So we've got an ETA here, which stands for estimated time of arrival. There's about 12 seconds left in this first epoch, as long as everything goes to plan. And so you can see the loss has reduced slightly and the accuracy has increased. So this is a good thing. Now what we should see at the end of this first epoch, if we set it up correctly, we should see, this is loss on the training set and accuracy on the training set. We should see the loss on the validation data and the accuracy on the validation set pop up any second now. So we're just waiting. So probably what it's doing now is it's been a little bit longer than 12 seconds, but it's loading the validation data into memory so it can calculate and evaluate how it's performing on that data set. I can't believe we're doing this. We're like training a model together in real time. This is phenomenal. I've never done this before. That is as long as your code's working. Here we go. Look at that. So now we have, this is what I was talking about. We have this metric is on the training data and this metric is on the validation. So see how quickly our accuracy is improving? Now I told you, epochs are going to speed up. Look at that. The first one took about 5 minutes, but these are taking 5 seconds. We're already at 1.0 accuracy. That's 100% accuracy on the training data. That is insane. So what this is telling us actually is it's a good thing. Our model is overfitting because it's performing way better on the training data than it is on the validation data. But this is great. Our model is working. It's finding patterns. It's using what MobileNet v2 has learned in ImageNet, and it's applying it to our dogs data set. Dog vision is coming to life. Oh, I'm so stoked. Now, I hope yours is running like this as well, because we're training a model together in real time. This is beautiful. So what we should see is once the validation accuracy stops improving for a number of epochs, so 3, because of our early stopping callback, it's going to stop training. So we actually, I don't think we'll reach the 100 epochs, maybe not even close. Because see here, we're getting 1.0 accuracy with a tiny loss on our training data. So here we go. It stopped. Whew. My heart is racing. That was phenomenal. So see what I meant? The first epoch takes a while because it's loading data into memory. Once it's loaded that initial data in the memory, the GPU is just going to go, all right, time to step on the gas and we'll turn on the afterburners. All gas, no brakes, baby. So we reached 18 out of 100 epochs, and we can see that our model on our training data set is performing at 100% accuracy. That's pretty crazy, 1.0. You got to times this number by 100. The loss is fairly low. I mean, a loss of 0 is perfect. But we can tell that our model is overfitting because it's performing way better on the training data than it is on the validation data. So if we come back, it's like our model has memorized the course materials rather than the problem-solving principles of those course materials, and it's struggling to adapt to a data set it hasn't seen before, aka a practice exam or our validation set. So right now our model has a poor ability to generalize. Whew. So I think that's enough for one video. That's a lot of excitement. What I want you to do, a little bit of homework, is before we go and check the TensorBoard logs in the next video, because we've used our TensorBoard callback before, I want you to check out, this is a question. This is a really important one. After we've trained a model, I want you to go, question, it looks like our model is overfitting because it's performing far better on the training data set than the validation data set. What are some ways to prevent model overfitting in deep learning neural networks? So we'll turn that into Markdown. That's a question I want you to look up before we get into the next video. What are some ways to prevent model overfitting in deep neural networks? So check that out. Even if you're not sure of them, I just want you to start getting curious about what's going on. And I want you to start picking up on the clues as to when your model is overfitting, such as performing far better on the training data set than the validation data set. And a little note here, overfitting to begin with is a good thing. It means our model is learning. So that I'm phenomenally excited that we have just trained our first deep learning neural network together using transfer learning. Dog vision is coming to life. So we finished training a model, at least a first subset of a model. This is not on the full data. This is only on 1,000 images. So our next step is to, if we come into our keynote, what are we up to? So we fit the model to the data. We haven't made a prediction yet. So what we might do is evaluate the model using our TensorBoard callback, so you can see that. And then we'll figure out how to make a prediction with our trained model. Sound like a plan? So check out this question, and I'll see you in the next video. Now we've trained our first model, congratulations by the way, a good idea is to evaluate how it's going. And of course, we could look here, we can see the accuracy, it's getting pretty high. So the accuracy 100% on the training data set, but only about 63% on the validation data set. It's overfitting, but that's a good thing, right? Overfitting to begin with means our model is learning something. But since we've set up a TensorFlow callback, we can now utilize our logs folder. So if we go into dog vision and we go to logs, see how we've got two files there? This is from, I trained our first model yesterday. So this is where we've got logs from yesterday. And this is today's model. So, or the one that I've just trained when I had to reset this notebook. And so what we're going to do now is load up TensorBoard so that we can check out these log files and see how our models are performing. Now this is helpful if you're training more than one model. Of course, we can just, as I said, refer to this. And then if we ran another model, maybe down here, if we did model 2 equals train model, we'd get this output, this verbose output is what it's referred to. And we could just compare these two cells, but that's not going to really work over the longer term. So that's what we're all setting ourselves up about. So let's write a little heading here. Actually, we might do it in this cell. So we'll go checking the TensorBoard logs. And the beautiful thing about setting up this, like a TensorBoard callback, is that whenever we train a new model, it's going to automatically log its performance. So let's do a little right here. We go the TensorBoard magic function, percentage sign there, TensorBoard will access, we have to pass it the logs directory, but it will access the logs directory we created earlier and visualize its contents. We'll turn that into Markdown, Command MM. Colab cell shortcuts are slightly different to Jupyter. We go TensorBoard. Now, this is the magic function I was talking about. We have to pass it, the tag, to our log directory. And if you remember, we saved our logs. We just saw that. We just have to pass it the file path to here. So we could copy that, but remember we're in the habit of typing it out. And now, because this magic function is as if we're running it on the command line, we're not going to pass it the file name, the file path as a string. We're going to pass it as just non-string, just as if we were running this on the command line, writing it in terminal. So if I show you terminal, so just if we were running cd desktop, I'll zoom in there. See how desktop isn't in string format? Just the exact same there. So drive, my drive, and now the trick here is because we've got a space in my drive, we need to escape it using the backslash. So my drive, and then we're gonna go /, we need dog vision, again, another space here, dog vision /logs. So hopefully, this should load in to the dog vision logs folder. Launching TensorBoard, yes, that's what we're after. So this is a great tool to help us visualize how our experiments are going. It might take a little bit to load for the first time because you're going to see it's going to be a fairly graphical interface. Check that out. There we go. So see here on the left, let's just have a look at this interface. We've got a few options, TensorBoard. We've got inactive because this will actually update if we're training a model. We can refresh it if we want. If we come down here, these are the experiments we've run so far. So there's today, it's the 5th of February 2020, where I live right now. I just ran these. And if we turn off these are from yesterday. We're only going to get 2 graphs here. And one of them is the validation data set, so the validation performance, and the other is the training set, so the epoch loss. So these are epochs down here, and this is the loss value. Let's go back up. So remember the loss value we're trying to minimize, while the accuracy we're trying to increase. So if this epoch accuracy, if this is going up, that's what we want. But you see here how the training data set, the one in the red, is going up way further, almost to 1 compared to the validation data. That's where we can tell that our machine learning model is overfitting because it's learning the patterns in the training data far too well. So a later experiment would be trying to stop our model, our machine learning model, from overfitting. So one of the ways we can potentially do that is by using more data. So we'll try that later on. But as we ran more experiments, as we keep using our create TensorFlow callback, it's going to continually store logs in the logs folder. And now that way, if you find that one machine learning model, if we turn these back on, if you find that one type of model is really outperforming, so let's have a look at both of them just on the training data sets. So if we look here, they're basically following the same path. Going down and down, that's with the loss. So the loss is going down, that's good. It means our model is learning something. And if we follow this, they're also following the same path here, which makes sense because we're using very similar data. Oh, well, because we set a random state way back up when we split our data. we're actually using quite the same. Right back up when we created our validation set. See how we use random state? So both of these experiments are using the same sort of data, so it makes sense that they get very similar results. So again, you can call this whenever in your notebook, whenever you've run an experiment. And that way, you can check out, okay, if I know I ran this experiment here, I can see, all right, so that model that we ran with these different values here in our create model, it got a certain results. And then if we altered this, we could see how that changes the results. So you can start to see over time how this gets more and more valuable at tracking your experiments and seeing how it does. Alrighty. So now that we've seen TensorBoard, we've seen how we can track our experiments over time. What I believe our next step is to do is to use our trained model to make some predictions. So let's do that in the next video. So we've seen how we can evaluate our model's performance, or at least initial performance, on something like epoch accuracy and epoch loss, and see how we can track different experiments. But this is just on the model's training and validation sets. And it's only really on what the model has learned in the data set. What are other really good way to evaluate what our model has learned is to use it for what we're building it for. If we're building dog vision, and we always got to keep in mind what the end goal is with whatever project we're working on. We're building dog vision to see if we can build a machine learning model that can identify a dog breed in a photo. So it's going to make some predictions giving a photo. So let's do that. If we come back to have a look at our workflow, well, we fit the model to the data. Now it's time to make a prediction. So we're still in step 3. We've done a little bit. We've touched on step 4. And remember, these aren't really linear steps. So these are just, I've just put them here because it's easy to understand it like this. But remember, they aren't necessarily linear, so you can do them out of order. We come back, we'll make a little heading. Making and evaluating predictions using a trained model. Command MM for turning it into Markdown, Shift and Enter. Okay. So making predictions with a trained model is very similar to how we did it in scikit-learn. So we can call the predict function and pass it data in the same format the model was trained on. That's the important thing. Let's see the code first, and then we'll discuss what's happening. So make predictions on the validation data. So remember, we created a validation data batch. Now, this was not used to train on. That's the important point. If we come back to our 3 sets, how we evaluate a model is because it trains on the training set. We want to check it out, its initial results on the validation set, and then both of these exams, so the practice exam and the final exam, are data sets that the model hasn't seen before. So we come back, let's go model, or actually we'll save it to predictions. Predictions equal model.predict val data, because let's just remind ourselves of what val data is. Val data, batch data set, there we go. We've got some images and some labels. So we know what the true labels are of the validation. So when we pass this batch data set to model.predict, because of the nature of the predict function, it's only going to look at the images in val data and then make predictions based on those images. So then what we can do is compare those predictions, which are going to be in the form of labels. Well, not exactly. We're going to see what they look like in a second. We can compare the model's predictions that it makes on the validation images to the actual labels from the validation images. Now, that was a lot of talking. It's much better to see this in code. So verbose is just going to say, hey, when you're making predictions, show me your progress. Well, that was really quick because we've got 200 images. So that's the beauty of working on a GPU. Predictions are really fast as well. And so that only took about 187 milliseconds. So not even a whole second. And if we didn't set verbose to equal 1, we wouldn't get this little progress bar outputting. You might be looking at this and going, what is going on here? Lots of just different numbers. So let's check out the shape here, prediction shape. If you remember, where does this line up? So if we go len y val 200. So there's the first shape. So 200 images. Where do you think the second shape is coming from? 120. Where have we seen that before? Len unique breeds. 120. So this means that we've got an array of 200 by 120. So we have 200. Let's see the first element. So we have 200. We'll go predictions 0. 200 arrays of 120 different numbers that are really small. And we're wondering what is going on here. Well, let's find out the length of this. 120. Wonderful. So what this actually is an associated probability for the likeliness. So basically what our model thinks a certain image is. So there's a probability value here for every single label. So the value here, the highest value in this predictions array, so the 0th predictions array, this is for one image, the first image in the validation data. So the highest value in here is going to correspond to the index of the label that the model thinks is most likely. And again, this is a lot of talking. It's going to make a bit more sense once we start to put it together with code. But just bear with me for a second. If we sum up all of these, they're going to equal very close to 1, or maybe 1 exactly. And I say very close because the way computers store numbers is not exactly. So if you keep going decimal points, right, it's going to get very close to 1, but it might not be exactly 1. And you might be saying, Daniel, what are you telling me this? The way the computers store numbers is not exact. Well, I don't even fully understand it, but you just have to know that when a computer stores a number that has lots of decimals, because of the way it's most efficient to actually store it on a computer chip, it's not going to be perfectly exact. So that's why I say when you sum up a single prediction array, it's going to be very close to 1. And now I'm going to tie this back up into where we've come back into our model. This is why we've used softmax activation. You might be saying, Daniel, far out. This is videos ago. You've already told us about softmax. It didn't really make sense, and it's really not making sense now. But if we go back to softmax, we just go, yeah, how about we go, what is softmax? If we come back to our friendly Wikipedia page, it's going to tell us that, but after applying softmax, each component will be in the interval between 0 to 1, and the components will add up to 1. So that is what we're getting here. We're getting our components, because we've used a softmax activation in the last layer of our network, it's outputted an array, a prediction array, that is 120 in length, and all of these values in prediction 0 and each other prediction here. So predictions 1 will be very close to 1 as well. So predictions 1 add up to 1. Or very close to 1. Oh, predictions. There we go. See, this is just over 1. So very close to 1. The more decimals there are, the less exact a number is with a computer. And so let's put this all together. Because right now it's just been a lot of talking. I want to show you a concrete example. Let's take prediction 0. So we're going to remove these cells. And just one little tidbit as well. Remember our MobileNet v2 architecture? All that our softmax layer is doing is taking these 1280 output, this array of numbers, and changing it into an array of numbers like this, of length 120, using a softmax activation. Because remember, for multi-class classification problems, we want a softmax activation. But if we were doing only single classification, we'd use sigmoid. So we come back here. Let's check it out. So the first prediction, I'm going to type out a few little indexing tricks here. And I just want you to just watch on. I'll talk through it a little bit as it goes. but I want you to start thinking about how these things all tie together. So let's do it. Because what our goal now is, our model has made some predictions here, but our goal is to understand these predictions further. So our computer understands these, right? Because they're all numeric. So remember at the start how we spent a lot of time turning our data into numbers? Kind of when you get to the output of a machine learning model, right? So this is what we're focused on. We spent a lot of time preparing our inputs. Now we're going to spend a lot of time preparing our outputs, which is what we're doing now. So let's go print prediction 0. And then what we're going to do is go find the max value probability. So remember the function in scikit-learn you might not called predict proba, which outputs a prediction probability. This is what predict does by default in TensorFlow. We go here, prediction, NP, max, predictions 0. So we're finding, let's remind ourselves, prediction 0, what it looks like. We're finding the max value in here. That's all that line does. And then what are we going to do next? So print, we want to, what else do we want? We want to find the sum. So NP, or actually, we might set this up so we can do multiple. So index equals 0, just so we can see it with multiple examples. So the sum. Sum is going to be NP sum, predictions, index, nice and simple. Then we're going to go, wow, that was a terrible typo, Daniel, come on. We're going to go the max index. So find the index in this array which has the max value. So which is equal to max value. NP argmax, predictions, index. And of course, what we're doing now is a little bit tedious. We're going to functionize this later on. So you could imagine if we just kept writing cells like this is where we're functionizing all of our code as much as we can, so that we don't just have to continually write these type of print statements to explore our data or explore our predictions. Predictions, index. Wonderful. Predicted label. Now before we run this cell, we're going against our cardinal rule of if in doubt, run the code. I want you to just have a think about what this one is doing. Let me remind you of what unique breeds is. So these are all our dog breeds. So if we have predictions and we find the max index of it, and then we find where that index occurs in unique breeds, what do you think that will return? Hint, we've typed it out here. All right, let's delete this bad boy, and then we'll shift and enter. Wonderful. So here's index 0. This is that array, just the exact same here. The output of our model when we call predict. So the max value, the probability of prediction, the maximum this can be is 1, because remember, the total of a softmax function is between 0 and 1, so the highest a single value can be is 1. So this is saying we're predicting the highest label in here with a 21.6% prediction probability. Now the sum of all of these values is very close to 1, again, aligning with the softmax rule between 0 and 1, and will add up to 1, but because of how computers calculate numbers, not exactly 1. And the maximum index, so where this value occurs, is 17. So if we counted through, we find 17, it's somewhere maybe there, that's it. Now, the predicted label is border terrier. So for index 0, or for validation image 0, the predicted label is border terrier. Now let's change this up. What if we did index, what's our favorite number? 42. So we got max value, probability of prediction. So this is a lot higher. This is 75%, so it's pretty confident with this one. So you could say the higher this value is to 1, the closer it is to 1, the more confident a model is about a certain prediction. The sum is very close to 1, the maximum index is 113, and the predicted label is Walker Hound. So if we go here, unique breeds. If we were to find index number 113, we would find Walker Hound. There we go, Walker Hound. 113. Walker Hound. So this is how we convert our prediction probabilities in numeric form, something that our computer understands, to something that we understand, a predicted label. So now we've got a kind of way to turn our predictions into something that we can understand. What we'll start to do next is we'll create a bit of a function that's going to allow us to find the predicted labels for every sample in the validation set. So about 200 or so images. And then we're going to unbatch this data set, the validation data, and compare the predictions in a visual way to the truth labels. Now again, a lot of talking, but in the next video, we'll start to build out that functionality and we'll see what it looks like in reality. And I'm so excited, right? Because one of the funnest parts is comparing your model's predictions with what's actually going on. Dog vision is coming to life. So in the last video, we talked about how we can convert our model's prediction outputs, aka this long list of numbers that are really hard to understand if you're just looking at them for the first time, into something that we can understand, a predicted label in the form of a string. Well, what we want to do is to make it a little bit more visual, because this is pretty tedious, just comparing it like this. So we'll create some functions that are going to help us basically do this step, as well as visualize the actual image that a model is making a prediction on, and then compare it to that image's actual label, or the truth label. And just a little tidbit, these are also known as confidence intervals. If you hear them, this is a prediction probability. There's also confidence interval. So one methodology of evaluating a model is to go, okay, only give me the predictions that have a confidence value over 0.75. Every prediction that's max value is under 0.75 gets pushed to the wayside. Those are things you might want to pass to a human classifier, but everything over 0.75, you might want to let the model predict itself. Let's write a little note to ourselves. Having the above functionality is great, but we want to be able to do it at scale. And it would be even better if we could see the image the prediction is being made on. Part of being a data scientist or a machine learning engineer is not just being able to write this sort of code. A more important step than building a machine learning model is evaluating it. So this is what we're kind of doing. We're communicating to ourselves what's going on. Because it's one thing to just show someone an accuracy score. We could just go, yep, there you go. Our model's accuracy is 100% on the training set. And they might go, whoa, okay, let me see what's going on. So that's what we're doing. We go here. So if you had to report it to someone else, or if you had to show a colleague, or maybe you're partnered with a business who doesn't really know what you're talking about when you tell them the probability of prediction is 0.75, it's much easier when you can show them something visual. So we go here, note prediction probabilities are also known as confidence levels. Markdown, wonderful. All right, so a little function, let's go turn prediction probabilities, which is what we have up here. These are all probabilities. So if you hear me say prediction probabilities, I'm referring to a long array of numbers like this that are probabilities. And we go here, turn probabilities into their respective label. Easier to understand. So we'll go def get, we might do it of a single one. So maybe get pred label. We'll pass it a prediction probabilities array, which remember is just this. Prediction probabilities. Because what we're doing here, remember our goal is to just functionize this ugly print statement. Well, it's not really that ugly. It's actually some pretty neat code, but we want to make this available to us at scale. Prediction probabilities, yes. And then we want to leave a little doc string for ourselves. Turns an array of prediction probabilities into a label. we can just do a simple return statement here, unique breeds. All we want to do is index the unique breeds for the argmax of prediction probabilities. Again, we're just replicating this one here. All we're doing is we just want the predicted label from this list of numbers. Let's see what that looks like. If we want to, let's get a little example. Get a predicted label based on an array of prediction probabilities. Typos galore. Pred label. Get pred label predictions. Let's go on the first index. So all we're doing, we're just calling our function, our beautiful little function that we've just written. And hopefully this returns us the pred label of 0. Border terrier, that's what we're after. 9. What's your favorite number? Mine used to be 81. Because 9 times 9 is 81, 1 plus 8 is 81, 8 minus 1 is 7. I have a dog called 7. And I had a Snorlax level 81 once. I traded it to a little American boy who was a mate of friends with at a resort. His name was Gareth, and he left the resort without ever trading back my Snorlax. So that was the end of that story. All right, wonderful. We've got a list of different predictions that our model has made, and we've got some functionality to turn those prediction probabilities into a label. So we're making our predictions more easier to evaluate for our eyeballs. We've already got some metrics on them with TensorBoard. Now what we'll probably do is, since our validation data is in a batch form, so it's a batch data set, we want to get a list, we want to unbatch it basically, because we want to rip out those images. So we want to get these images out of here and these labels, because these are the truth labels. That way we can make predictions on the validation images and then get our prediction labels using our function, and then compare those prediction labels to the actual validation labels. So let's make a small function which does that. So what we'll do, we'll go here. Now since our validation data is still in a batch data set. Remember, it's in a batch data set because that's very efficient for TensorFlow to make calculations on. We'll have to unbatchify it, and just made that word up, to make predictions on the validation images, and then compare those predictions to the validation labels, truth labels. This is going to be really cool once it's up and running. So let's write here, create a function to unbatch a batch data set. The people who make TensorFlow have actually thought about this problem. Well, not even a problem, it's just a little roadblock, because if you've batched a data set, surely there's a way to unbatch it, and there is. If we go TensorFlow 2.0, unbatch. Where is it? Dataset, unbatch. Unbatch, here we go. Splits elements of a dataset into multiple elements. For example, if the dataset elements are shape B, something, 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 where B may vary for, I'll let you read that if you want. But basically we've got elements here. TF dataset from generator, dataset.unbatch, list dataset as numpy iterator. So once we've unbatched it, we can call as numpy iterator, and it's going to turn it into an iterable list. So again, if this code doesn't make sense when you first read it, the best way to figure it out is to write it. So let's do that. Let's write it in a non-function first, and then we'll functionize it. So images, because we want to get the validation images, or we want to unbatch these. We want to get these and these into separate entities, not one. Labels, we'll make an empty list. Oh, maybe these are, I don't want to override a variable I have before. So images, we'll just underscore them. There we go. Then we want to loop through unbatched data. So we go image label, right? We've got a tuple here of image label. In val data.unbatch. So all I'm doing, calling unbatch. And I'm going to do these in one hit. So I'm going to call unbatch and dot as numpy iterator in one hit. So let's see what happens. If we go print image, this might actually bust our computer, but we'll see it anyway. If in doubt, run the code. What's it going to return? Boom. So there we go. It's going to go. That's going to go for 200 or so because that's how many samples are in our batch, our validation batch. But all it's doing now is printing out the image and the label, the image and the label, the image and the label. But the image is, remember, in the form of a processed image, a pre-processed image, which is that pre-processed image function we wrote right at the top. We don't want them just like that. We want to append them to our list of images. So append image and labels dot append label. So now what we should have, if we go images 0, image is 0. So there we go. So there's one image. And its counterpart label, we should have just done that at the same time. Label 0. Why didn't that come out? Oh, that's why. Labels. See, confused myself with the variables that we're saving. This is why it's helpful to functionize things, because if you create different variables and you lose track of what variables they are, you'll confuse yourself. There we go. So there's the true label. So this is image validation 0 and its ground truth label. So our goal is to visualize this image and compare this ground truth label to the prediction label that it's made. So we could go get pred label, labels 0. Wonderful. Can't. What the prediction label was, so we could go get pred label, predictions 0. Border terrier. So that's a prediction that our model got wrong. So this is what we're trying to visualize. Right now, that's not really that fun, and we want to make things fun. So let's functionize this, and then we'll finish the video there. Actually, that's a challenge. Before I go off and start functionizing this little sequence, I want you to give it a try. Call the function something cool, like unbatchify, and it should take an input of a data set, a batch data set, and it should do this functionality and return these two lists. So that's your little challenge. I'll give you a couple of seconds. All right, I'm back. Didn't really leave, I was here the whole time. Hopefully you had a little try of functionizing this beautiful unbatchify function that we're going to write. So we'll write a doc string, takes a batched data set of image, label, tensors, and returns separate arrays of images and labels. Tick, tick, tick. And we want to create images. Because it's within a function, we can use whatever variable name we want. And then we're going to go loop through. So basically, all I'm doing is just rewriting this up here. Instead of copy pastoring, I'm just writing it out again because I want to practice. So for image label we only have to use data. So this is because I've set up a data parameter, so I can just pass it any batch data set I want. So data.unbatch as numpy iterator. Beautiful. Images.append image, labels.append label, and then we can return images labels. If we test out our little functions unbatchify, let's see what your abilities are like, unbatchify. Do you stand up to the challenge of unbatchifying our validation dataset? Equals unbatchify, and we're going to pass it our val data batch. exactly the same as what we've done here. We just functionized it. And we'll check out val images 0 and val labels 0. Boom. So just the exact same thing there. That's what we've got here. One final check is we can get pred label. What was it? Can or can, maybe I'm saying that wrong. If we go here, so get pred label, val images 0. Oh, no, it needs to be labels. Oh, did that? Okay. That worked. Oh, no. So that's going to work because that's numbers as well. So we actually want val label 0. Can't. Wonderful. Okay, so now we have a function for unbatchifying our data. We can get our validation images, which is great. So we can now work out some little functionality to make predictions on those images. We can get the ground truth label and then compare that to the prediction label. Let's delete this code here and we'll finish up the video. And in the next one, what should we do? We should make some functions to plot an image. So visualize an image of a beautiful little dog. We'll also compare the truth label to the predicted label. That sounds like a plan to me. I'll see you in the next video. Alrighty, so now we've got a way to get validation images, validation labels, so aka the truth labels of what an image is, and prediction labels. So you might be thinking this is a fair few steps to visualize what's going on, but I hope you realize where the importance is, right? Because we're always thinking about what's the end use case. We're not just here to build models for the sake of building models. We want to build dog vision. To return, we could just return an array like this to a user. And then they would go, wow, I'm not going to use this app anymore because these numbers are just a bunch of jargon to me. So that's why it's important that we can visualize our model's predictions in a way that people can understand. Someone who isn't as versed in machine learning and prediction probabilities as us can understand. That's our end goal. And that's what I want you to start thinking about all of the projects that you're working on rather than just building models. What is your end goal? Are you working towards something? How can you communicate what you're doing to someone else? All right, so let's write a little note to ourselves. Now we've got ways to get prediction labels, validation labels, which are the truth labels, and validation images. Let's make some functions to make these all a bit more visual. Basically, we need a bit of color in our lives. Okay, now how might we do this? So we're probably going to make a function, as we said before, that's going to show us an image, and it'd be good if it could just plot that image. That's what we can use, matplotlib, something like that. Take an array of image values, which we've got here, maybe a good thing we work towards is it plots the predicted label, its predicted probability, so the max value up here. So something like this. So this is 75%. And then its actual label. I think we can get them all onto a single plot. Maybe we'll write that down. So we don't confuse ourselves. Remember the rubber ducky technique from my boy Ron? Thanks, Ron. We'll create a function which takes an array of prediction probabilities, an array of truth labels, and an array of images and integers. Now again, I must stress, I'll say it till I go hoarse, but we are dealing with images, but the visualization steps that we're doing goes for almost any data that you're working with. So we're going to go convert the prediction probabilities. Of course, you may need to use some other visualization techniques that aren't matplotlib to plot or to visualize a data sample, but you get the picture. Predicted label, and plot the predicted label, its predicted probability, the truth label, and the target image on a single plot. Okay. So, how might we do that? Let's go here. We'll call it def, something simple, plot pred. It takes, what does it take? It takes prediction probabilities. It takes labels, an array of true labels, and an array of images, and maybe only one integer. Let's make this so it plots a single image, a single prediction label, and a single truth label, and an integer. So maybe we could just save this as n equals 1. That's going to error out because we've got nothing there. That's all right. Get rid of that error. We don't like seeing them. They cause me a little bit of stress. So we go here. View the prediction, ground truth, and image for sample n. And again, getting trigger happy, right? It's like almost instinct for me to press shift and enter whenever I finish writing a line of code. Okay, so the first thing we'll need is the pred prob. It's actually prediction probability, but I'm not typing that multiple times. True label and the image. So this is going to equal, remember we want the nth sample. So we do have to actually type prediction probabilities. N, so the index, so the nth sample. And then we want labels n. And again, there's probably 1,000 ways to write this function. This is just one way that I figured works. Could be probably optimized in some way, but it works for now. Equals get pred label. Now that we have the prediction probability, we can use our function get pred label to get the pred label. Brilliant nomenclature of our functions, if I do say so myself. Plot image and remove ticks because we just want a square of images. We don't want axes. .im show image. So this is a matplotlib function. You pass it a numpy array if it's an image. Display an image, i.e. data on a 2D regular raster. Far out. Sometimes doc strings are written in a complex way. Like it could have just said plots an image. Y ticks. So this is just empty lists. So we're just turning them off. And, or basically it's just going to show nothing because there's nothing in that list. We might need the plot title. You're right. Change plot title to be predicted. We want predicted label, probability of prediction, and truth. Label. So plt dot title. Now we've got our pred prob, we've got our true label, and we've got our pred label. So we're just going to have to create a string of 3 of these. So pred, probability, and true label. Now this one is going to have to be 2.0. What is this doing? This is just reducing the amount of decimal points in our prediction probability so that it's not something long like this. Better example. It's not something long like this, it's a percentage. So rather than being that, it's 75%. That's what we're after. Come down here, we'll just do a little format. And we'll go pred label, because that's the first one, so prediction is there. And then we want np max pred prob times 100 times 1,000. Whoa. So this is just going to be the prediction probability value. So the max of this, of the pred prob array, times 100. So when we saw 0.75 up before, it's just going to times that by 100. Might not be 0.75 because it'll be a different value for each different image. There we go. And we want true label is the last one. So does that make sense? So plot title, we want to get rid of that pass. Plot title, squiggly brackets for pred label, squiggly brackets, 2 decimal places percentage for the maximum prediction probability, and squiggly brackets for the true label. Let's see what this bad boy looks like. Unexpected. End of string. Oh, we need another one. Plot pred. Okay, and now let's go. Plot pred. We want predictions. Oh no, prediction probabilities equals predictions. And then we want labels equals val labels. And images equals val images. So this is just from up before where we unbatchified our validation data set we've got here. And let's come down. Let's test out our little function. Oh! Now our labels are printing out incorrectly. What's happened here? True labels equals pred label. Get pred prob. What is happening here? True label. Well, we didn't convert. I think I see what's going on. What we have to do is convert our true label into an actual label. So right now, this is debugging your own code, right? So what we have to do is change our unbatchify function to be unique breeds, and this is going to be np argmax label. Does that make sense? Yes. So just a very similar functionality. What we could actually do is use this function here, get pred label, but we might save that just for predictions. So this is going to get the unique breeds np argmax label. We need to rerun this. So make sure you update your unbatchify function. And then if we rerun this should be correct. And then if we rerun this, oh yeah, Scott Terrier, 68% correct. This is not very intuitive. What if someone was looking at this and it was like Scotch Terrier, 68% Scotch Terrier? Which one is the predicted and which one is the non-predicted? Let's add some color. That's how we could do it. So what we will do, we'll create a little if-else clause. So we'll go change the color. Oh, that looks disgusting to me. OR. See, I'm Australian and we spell colour O-U-R. So whenever I see OR, even though that's the actual little parameter that we have to pass to format, I don't like it. Colour of the title, depending on if the prediction is right or wrong. So all we're going to do is change this title to be green if it's right and red if it's wrong. Pred label equals true label. We want color equals green, else color equals red. And then we're going to pass a little parameter here. So it's all about making our plots more visual. Uh-oh, what? Why didn't that change? If pred label equals true label, Oh, there we go. I found it. So that's part of the format. We need to pass this outside of the format. Does that make sense? So we're passing this color parameter directly to title rather than to format. Scotch Terrier 68%, beautiful. Now remember, this is predicting for index 1. So what we might do is just make sure it works on another image. What's our favorite number? 42. It got that one wrong. That's a good example, actually. It's pretty confident, 76%. It predicted Walker Hound, but it's actually an English Foxhound. So let's look up English Foxhound. What does an English Foxhound look like? Images. Okay. We go back to dog vision. Wow, you can kind of see how they look pretty similar, especially that part on the back. Those two there. See how that's black there, and that's black there? So you can kind of see, oh, look at these puppies. This is the beautiful thing about working on a project dog vision. You get to look at dogs. So you can kind of see where that's going wrong. Let's look at one more. My other favorite number is 7, so why not 77? And I got that one right. That's really confident. That's awesome. A growing endial. Well, this is very exciting because now we're actually seeing our model's predictions compared to actual images. Dog vision is officially coming to life. This is the kind of functionality we wanted from the very start, to be able to pass our model an image and it make a prediction. And now we're seeing how confident it is on that prediction. So prediction probability or confidence interval, and we're actually comparing it to the real label. So this is an image, because it's from validation dataset, an image our model has never seen before. So you better pat yourself on your back because you've just built a deep learning model that's able to take photos of dogs and predict what kind of breed it is. That's pretty cool. Now, one more thing we'll probably do to visualize it a little bit more is see what other labels our model predicted. Because there's prediction probabilities for every label, it'd be interesting to know what other dog breeds our model looked at an image and thought it was. So this one's 96%, so that's pretty darn confident on it that it's a Groenendael breed of dog. I can't even pronounce some of these breeds of dogs. Well, let's do that in the next video, hey? We'll create a plot to show the top 10 predictions. So we've really started to evaluate how our dog vision model is going by visualizing our model's predictions. I just want to give you a little challenge before we get into this video, which is saving and reloading a model. What an interesting thing might be is now that we've visualized the images, the predicted label, the predicted probability, the true label, and the top 10 predictions, how could you make a confusion matrix to figure out where your model is confused with what we've got? So remember, a confusion matrix is comparing the predicted labels to the true labels and then seeing which ones the model gets confused, because that would probably be really helpful with this sort of problem and helpful with any kind of multi-class classification. So that's a little challenge to you, a little bit of extracurricular. I'll put it here. Before we save and load a model, let's go here. Challenge. How would you create a confusion matrix with our model's predictions and true labels? So if you do figure it out, make sure you share it in the Discord chat. You can share your work and help others if they're trying to figure it out as well. With that being said, good luck with the challenge. Let's create a little title for saving and reloading a model. Now this is helpful. Of course, it's taken us a while to get here, so it makes sense to want to save our progress after we've trained a model. Let's figure out how we would do that, a trained model. And it also helps if you wanted to share your model. So say we wanted to export our dog vision prediction capability to someone else. We wanted to put it in a web application. We might need to get it out of our Colab notebook. So that's what we're going to do here. TensorFlow, how to save a model. So this is what I would do. Oh, that guy's really excited. Just like me, just like us. Let's save and load models. Again, we could read through here. But what we're going to do is we're just going to write the code first, and then if you want to read up on a little bit more, you can read through the documentation here. So we'll create a function to do it so we can call it on any model. So create a function to save a model, and we'll do it nice and simple. Def save model, pass it a model, and suffix equals none. You'll see what suffix means in a second. So just like our log directory in Dog Vision, we might create a new folder called models. And what we're going to do is, as you might have guessed, is save, we've got our training logs here, and save our models to Dog Vision. So we keep it all within that one project folder, sticking with what we've got in our project setup. Create a project folder. So this is going to go saves a given model in a models directory, and appends a suffix, string. Nice and simple. So if we go here, let's create a model directory, path name, with current time. So just like our TensorFlow logs callback that we created a few videos ago, we want to, first of all, save our model with the current time so we can track our experiments. And we're going to give it a little suffix so we also know a little bit about our model, so we're not just opening our models folder and it's just timestamps. We'd also like to know how many images was it trained on and stuff like that. So that's what we'll do. We'll go model dir equals os path dot join, just like our TensorBoard, my drive slash dog vision slash models, and then we'll append. We'll join it up with the current time, which we can use datetime for that. So datetime.datetime.now.string from time, and we're going to go year, month, day, hour, month, or minute, second. Okay, beautiful. But now we also want model path, where we want to combine the model directory with our suffix. So model dir plus hyphen plus suffix plus dot h5. Now, if you're wondering what h5 is, that's the save format of model. It's just a file specification, just like JPEG. And if you read through the documentation, it's somewhere here. Let's go h5. There we go. Save weights with a h5 extension. There we go. So that's going to be the extension. And we just want to print a little update for ourselves. F saving model to, we'll go model path ... just to let us know that it's in progress. And we'll go model.save. So there's a method called save that you can call on a model, just like model.predict. And you pass it a file path. Let's see if the documentation will come up. There we go. Saves the model to TensorFlow save model or single HDF5 file. So that's what I meant by H5. So that's what we're doing. And then return model path, because we want to see the model path and we can use that later if we want. Okay. Now, we've got a function to save a model. While we're here, we'll build a function to load a model, because if we save a model, we want to potentially load that back in. So it makes sense to load our trained model. And then we'll test them both at the same time. Create a function to load a trained model. So this one's going to be very similar to what we do. So we go def load model, and we want to pass in a model path. So it's just like, hey, we've saved a model. This is why we return the model path. We've saved a model to this file path, which is going to be our models folder somewhere here. And so to load model, we want to go, okay, what can we call? We can go loads a saved model from a specified path. And then we go print f loading saved model from, where's it loading it from. So this is just for our own sanity to make sure that we're loading the right model. Model.tf.keras.models.load model. Again, saving and loading models, you would find this load model here. So load model, there we go. Recreate the exact same model, including its weights and the optimizer. So because we've used TensorFlow Hub, we actually need to do a little special thing here. So model path, custom objects. So this documentation, a lot of Keras and TensorFlow documentation is of the simplest use case, but since we're not using the simplest use case, we're using a TensorFlow Hub model. We need to pass it this little custom objects dictionary. So Keras layer, we just need to tell it, hey, we've got an irregular layer, so a layer you wouldn't have seen before in our model. And that's all we have to do. So all we're doing is loading a model from model path and saying, hey, we've got a custom little piece of equipment in our model. In particular, where is it? Right back up here. Look how much we've done. You should be really proud of yourself if you're watching this. Hub.Keras layer. That's all we have to do. So instead of just using these kind of layers, which are the traditional Keras layers, TensorFlow, we're using this special one. So that's what we're telling this load model function. And then we want to return the model. So now the ultimate test. Let's put it here. Now we've got functions to save and load a trained model. Let's make sure they work. So what we'll do is we'll save our model. Trained on 1,000 images. So this is where the suffix comes in. So because we trained it on 1,000 images, we want people to know that this is only 1,000 image, or we want ourselves to know that this is only 1,000 image model. Suffix equals 1,000 images, and we'll probably put Atom there for Atom Optimizer in case we wanted to change it. You could really put whatever suffix you want here. 1,000 images, MobileNet v2, Atom. That's probably nice and simple. So let's see what this does. And again, this is just a communicative part, not 100% necessary, but I found in practice it's very good to communicate, just even if it's to yourself, as well as if you wanted to share with someone else. They wouldn't just look in your models directory and go, hey, which model is which? They could go, oh, there's a suffix here, and then maybe you could tell them about that suffix. Saving, oh, unable to create file. What's happened here? You know what? It's exactly what I thought. Look at that. What's wrong with that? Classic. So these, trust me, you're going to run into these errors. These and reshape errors, getting your data into the right shape, are going to plague you for your entire machine learning career. Typos are a programmer's worst nightmare. So we go here. Oh, there we go. Saved. So there's our file path to the model. And now if we come up here into the models directory, there we go. There's our saved model. So .h5, wonderful. So if we X out of that, let's now test our load model. So load a trained model. So all we have to do is we're going to go loaded 1,000 image model. Long name there, but just for clarity. And we go load model. This is why we returned that. So we can just copy that there. We'll load that. Shouldn't take too long. Now, I'm probably going to have some warnings here. Yes. So, these warnings, what is it saying? Sequential models without an input shape passed to the first layer cannot reload their optimizer state. As a result, your model is instantiating. That's a fairly long warning. But if you come up to here and check warning, and I think it's one of the top ones. There we go. This may generate warnings if you load a model related to the saving state of the optimizer. These warnings and similar warnings throughout this notebook are in place to discourage outdated usage and can be ignored. So these warnings can be ignored according to the documentation. So it'd be helpful if they just remove them rather than just have them printed out. But aside from that, let's just see if it works. If it works, then we're all gravy. So evaluate the pre-saved model. Now another function you can call on your trained models is evaluate and pass it the data set, val data. And so we're going to run that. So this is our model before saving it, and this is our model after loading it. So evaluate the loaded model. Model.evaluate. Oh no, I nearly messed up. Went on autopilot there and started typing above the cell above. Image model.evaluate val data. So if all is swell, these should return the exact same thing. Wonderful. So this is just an evaluate function to quickly evaluate your model's performance on the validation set. And we can see here the loss is 1.2607, same as this, and the accuracy is the exact same. So there we go, how to save and load a model. Now we've saved and loaded a model, I think it's time. I think it is time to step it up and train a model. We've got it all working. Let's train one on the full data set. So get yourself ready, get yourself excited. I'll see you in the next video. We're going to train a model on the full 10,000 images. I hope you're ready, because now it's time to train a model on the full data. We verified that everything is working by going through, checking our model's predictions, evaluating them and going, yep, our model is definitely learning something, but since we've only trained it on 1,000 images, let's see if we can train a full-scale model, like our first full-blown deep learning model training on 10,000 plus images. And this is where the power of the functions that we created earlier are really going to come into play. So let's make a little heading for ourselves. Training a model. Actually, let's call it training a big dog model. And we might put a little emoji here on the full data. And you get it, it's a big dog model because we're training on lots of images of dogs. I love this project. Now, code. What we need is, remember right up the top, if you don't, that's okay, we're going to have a look at it now. We have X and Y. Len X, len Y. And this is all of our training data. These are the file names and these are the labels. So if we come up here, X is all of the file names in train. So if we have a look at the first maybe 10 of X, 10 of X, these are all our training image file names. We split these before into X train, which is only 800 in length. There we go. So if we have a look at len X train, only 800 images. So at the moment, our model has only trained on 800 images. And if we want to have a look at Y, Y is the labels associated with each file path in the form of Boolean arrays. So what do we need to do to train a full model? If we come back to our keynote, what's our workflow? Get data ready, turn it into tensors. Well, we've got a function for that. Do you remember create data batches? If you don't, it's all right. We've created a function for that. And we got pick a model to suit your problem. So TensorFlow Hub, we've got that. We can just use create model and then fit the model to the data and make a prediction. Let's give it a crack. So let's go create a data batch with the full data set. So this is where functions really help out, is later on in your notebook. I told you it was worth it. Full data equals create data batches. Look at this. This is our function that we've written above. Creates data batches of data of image X and label Y pairs. Beautiful. Shuffles the data if it's training, but doesn't. Well, that's a bit of a hindrance. We can't see that. Also accepts test data as input node labels. So that's all right. This is not training data. So let's create a full data batch. Now we have a look at full data. It's a batch data set. Beautiful, with images and labels. Wonderful. And if you're wondering what create data batches actually does, let's go right back up. If we have a look at our index here, what are we doing? Visualizing data batches, turn our data into batches. So here's our big function, create data batches. It takes X and Y. And here's what's happening. This is because it's a training data set. Creating training data batches. Turns X and Y into tensors. It shuffles them. And then it maps our processing image function as well as get label function to the data. And then it turns the data into a batch size of 32. But we've already seen a video on this, so if you need a refresher, go back and check out the video where we created this function. So let's come back to where we were. So now we've got our data batch. What's the next step? Well, we need a model. So let's do create a model for full model. Full model equals create model. Remember what our create model function did? Oh, no docstring. Well, let's run that anyway. We can go check it out. So building a model with tfhub.dev ImageNet MobileNet v2. So we've got a model. Okay, we've got a batch dataset and we've got a model. Now, if we want to check out what create model does, where is it? Building a model. If we come down here, this is our create model function. It doesn't have a docstring. Maybe that's something you could add. So create a function which builds a Keras model. So what it's going to go through is go through the steps that it took before to create a Keras sequential model using the model we downloaded from TensorFlow Hub and a dense layer on the top to make sure our outputs are the same size as the labels that we have. It's going to compile the model with a loss function and optimizer, which is our friend Adam, the guy at the bottom of the hill telling us how to descend down the hill at the International Hill Descent Championships. And metrics is accuracy is what we're measuring. And then we're building the model, feeding it the input shape, which is the size of our image. Wonderful. Come back. So how might we train this? What's next? What do we do next? Well, we created some callbacks. So we might have to make some specific callbacks for our model. So let's do that. Let's go create full model callbacks. Full model TensorBoard equals create TensorBoard callback. There we go. There's our function from before to create a TensorBoard callback. Remember, the TensorBoard callback helps us to track the performance of our model and compare it to others. And so there's no validation set when training on all the data. So with our early stopping callback, we can't monitor validation accuracy. So for our early stopping callback, we need full model early stopping equals tf dot callbacks dot early stopping. There we go. And we're going to get it to monitor accuracy. When our model is training on the full data, when its accuracy stops going up for 3 epochs, we're going to get it to stop training so it doesn't overfit, or we're going to try and prevent it from overfitting too much. So shift and enter. Wonderful. Seems like we might have a recipe to start training our model. So fit the full model to the full data. So here's where we can go. We can go full model dot fit. So we're just calling the model we created. Dot fit. X equals the full data. Now there's no validation set, remember, because we're training on the full data. Epochs is going to be 100, or it could just be num epochs because we've set num epochs before. And we're going to have callbacks, which are the 2 callbacks we've just created. Now this is just doing the exact same steps as what we've done training a smaller model, but this time with more data. Wonderful. And now I'm going to put a little note here to give you a little heads up, and well, I'm going to speak it out so you know as well. Running the cell below will take a little while. Maybe up to 30 minutes or maybe a little bit longer. 30 minutes for the first epoch because the GPU we're using in the runtime has to load all of the images into memory. So the first epoch, remember with our smaller model on 1,000 images, the first epoch took a couple of minutes, maybe 3 or 4 minutes. As you could imagine, because this one's on the full data set, it's training with 10,000 images. So it's going to take a little bit longer to load all of the data for the first epoch. So before we run this, as long as all the code's correct actually, it might error out. That's why, rather than train on the full data from the beginning, we've made sure everything works. Because when training a full machine learning model or a full deep learning model, it can take a fairly long time. And ours, we're pretty lucky here. This is going to train within an hour because we're using a GPU. But you could imagine if you're working at a bigger company, you might leave something training for a week. So that's why you want to make sure that when you set up experiments, imagine training a deep learning model for a whole week, and then it turns out that it wasn't working. So that's why we did all of the steps above to make sure that everything's working. So before we train a massive model, we can be sure, okay, things are in place. Let's kick off a full training round. So you ready? We're about to train our first full-blown deep learning model on 10,000 plus images. Dog vision is truly becoming a reality. Hit it with me. 3, 2, 1, shift and enter. Fingers crossed, hopefully this works. We should see a little loading bar come up. And because we've set number of epochs to 100, it's going to keep training for up to 100 epochs. But if it stops improving, we've got our full model early stopping callback that's going to stop it training early. And then we can check the results using TensorBoard after it's finished. So we'll just wait for this to kick off. And then what I'll probably do is pause this video because it's going to take about half an hour. I'm going to take a little break. Maybe you could too. Have a little walk around, chill out. Oh, maybe it's going to take a little longer than half an hour. This timer should go down unless my testing is incorrect, but we'll wait a few seconds. And then I'll come back to this video once the model has stopped. So once the model early stopping, the full model early stopping callback has kicked in. Okay, so I'm going to let this run for as long as it needs to run. I'll come back once my model has stopped itself, thanks to the early stopping callback. So I will see you in a couple of seconds, but for me, it's going to be a couple of hours in the future. Maybe it's a couple of hours in your future as well. And we're back. Alrighty, so let's have a look at our fully trained model. As you can see, my first epoch took a fairly long time. And this is actually, I need to take a moment. If you've finished this, if you've gone through this, you need to pat yourself on the back because this is like a rite of passage, training your first end-to-end deep learning neural network. And it's taken a long time. One of the things you'll have to figure out when you become a data scientist or machine learning engineer is ways to pass the time whilst your model trains. So I went for a walk with my dogs because this took what? How many seconds is that? So 4,730 divided by 60, 78 minutes. So just over an hour to do the first epoch, but as I said, after the images are loaded into the GPU's memory, check out how fast it goes after that. And what you'll probably want to do is as this cell is running, I should have told you this before, but you can take note for the future. As this cell is running, you want to have a save model running after it. That way, once your model stops training, thanks to early stopping, our early stopping callback up here, it's going to automatically call our save model function and save our full model to our models directory. Now let's come up here and have a look into models. Oh, I've got a few there. So let's see, it's going to be the one with the, there we go, full image set, MobileNet, 2nd of February. And I started at about 5 p.m. So this time is actually wrong for me because I'm not sure, maybe date time is getting the wrong time for me. But there we go, that's saved here. We've got our path. So now we can have a look. Our model actually ended up doing pretty well. Look at that, that's training accuracy. But I'm a little bit skeptic here. You know why? Because we aren't validating this. This is just a model training on the full training data. So let's come here. It's training on all the images in this train file, aka X and Y. And so we can't really test on a validation set, but what we can do is import the test data set that we originally downloaded from Kaggl. Here we go. The test file. And we can import those, turn them into a data bunch, and then use our model to make predictions and submit them to Kaggl. How epic is this? So our model is saved. Let's test our load model function. So loaded full model equals load model. We're just going to copy this path here. We'll go there, load in the full model. And if we copy this line here, tick. Oh, we don't want to put it there. We want to put it in here as a string. Let's check that out. Wonderful. That's going through. That's what we're after. So again, we're getting those warnings that the TensorFlow documentation says can be ignored. Alrighty. Now, what's next? Well, I think now that we've got a fully trained model on all of the 10,000 plus images, I think we see how to make some predictions on the test data set. So let's do that in the next video. So now we've got a fully trained model on the full training data set, aka 10,000 images, because if we look at X, we've got 10,000 images and labels. Now let's use our fully trained model to make some predictions on the test data set, which is also about 10,000 images. We'll have a look at that in a second. But let's come up to Kaggle and see how they want our predictions to look. So a submission file. For each image in the test set, you must predict a probability for each of the different breeds. The file should contain a header and have the following format. So we need ID, dog breed 1, I'm not even going to pretend I'm going to try to pronounce that once again, Afghan Hound, Yorkshire Terrier, and then the prediction probabilities for all of those. All right, now it says multi-class log loss. That's just the prediction probabilities for each dog breed. Create another header section, making predictions on the test data set. Now, I want you to have a think, before we go through the code, what did we have to do to train our model on the training images? Again, pretend this is data agnostic. Whatever data you're working with, whether it's text or audio or images or video or something like that, what is our rule before we can use it with a machine learning model? Or in our case, a deep learning neural network. We've got to convert it into numbers. So that's what we have to do. The exact same data type that our model was trained on. So the data batch up here, the data batch of images. We need to create one of those out of the test images so that we can make predictions on those images. So we'll write ourselves a little note. Since our model has been trained on images in the form of tensor batches, to make predictions on the test data, we'll have to get it into the same format. So if we come back to our graphic in Keynote, remember how I always said we're focusing on the input, so aka getting our data into the right shape for our machine learning algorithm, and then making sure the outputs are correct. This is what we focus on in the beginning. This has already been implemented for us in quite a large way. As we get deeper and deeper, as you get into further projects, then you might want to start diving into this. But for the time being, and for approaching your first projects like we're doing now, you're going to be focused on inputs and outputs. Now, a little tidbit here is, again, our functions coming in handy. Luckily, we created create data batches earlier, which can take a list of file names as input. If you don't remember, go back up to where we create data batches and convert them into tensor batches. So what steps do we have to do to make predictions on the test data? Let's write those down. To make predictions on the test data, now this is kind of what I do with a lot of my projects, is just talk myself through it, the rubber ducky technique. So get the test image file names. That'll involve us writing just a little list comprehension like we've done before to access the test. Go through all the files in here and save the file names to some sort of list. Yep, we can do that. And then we got to convert the file names into test data batches using create data batches and setting the test data. Remember how we created parameters in create data batches? If you don't, that's okay. We're going to see in a second. Parameter to true, because why? What's different about our test data to our training data? There's no labels with the test data. So since the test data doesn't have labels. And then finally, we make a predictions array by passing the test data batches to the predict method called on our model. Whew. We got 3 steps there, but we can do them. We can tackle them one by one. How about we start with the first one? That's pretty logical. Load test image file names. What could we do? We could go test file names, nice and simple, equals, actually we might set up the test path. How about we do that? Test path equals, and we'll just copy it here to save us writing it out twice. Copy path. That's a little handy tip you can do there. You can paste. We don't need content. We could just keep it there if we wanted to, but I'm going to remove it so it's consistent with the other paths that we have. And I'm going to put this one here. So that's my path to the test folder. So now we're going to go create a little list comprehension equals test path plus fname, file name, for fname in os.listdir test path. Now we've seen this before when we were creating the original training file names, but let's just remind ourselves what it's doing. So os.listdir is just going through, or list directory, that's what it's short for, is just saying, hey, Python, get me all of the file names in this folder. And then we're creating a list which appends the test path, which is this, or adds together the test path plus every single file name in the test folder. Let's have a look. If in doubt, run the code. Wonderful. So now we've got the file names towards our test data. We can tick that off. Get our green tick emoji. This notebook is going to be full with them by the end. Okay, now we've got it. What's our next step? Convert the file names into test data batches using create data batches. Oh, I said date there. That's wrong. There we go, we'll fix it up. First of all, let's just do a length check of our test file name, see how many images we have. 10,357. Wonderful. So now, to create a data batch, it's pretty simple. We just bring in our function, we go test data. We'll write a comment here before we get started. So create test data batch. And we're going to go create data batches. Oh, it knows what we're talking about. And then we're going to pass it the test file names. And we're also going to see there's our test data, boolean. So we'll go test data equals true. And we'll run that. Wonderful. We get a little printout saying creating test data batches. Such a great function that we wrote. Let's come up here and have a look at it again. Turning our data into batches. So we've got a function create data batch or create data batches. And what does it do? If it's test data, which it is, it prints out this little statement. And then it goes, hey, turn our file names into tensors and then use from tensor slices to convert it into a tensor dataset. And then create a data batch by mapping the process image function. Remember, we don't pass getImageLabel to the test dataset because there's no labels with the test dataset. So we process our images just like we did on the training data, and then we turn it into a batch. In our case, batches of size 32, so that it can be computed really fast on with our GPU. So let's come back to where we were. That's what we've got. And if we go test data, it's a batch data set of shapes. So there's no labels here. These are just images of 224 by 224 by 3 for the color channels of type TensorFlow float. So beautiful. We've got our test data in the form of tensor batches. That's what we're after. And now, the finale. We can come up here. See how handy writing our functions to begin with has helped us out. We've created a full model. We've created a data batch in one hit. Now we've got to make a predictions array. So how can we do that? Make predictions on test data batch using the loaded full model. All right, so test predictions equals loaded full model dot predict test data. We're going to set this to verbose equals 1. Excellent. Now, I kind of have to warn you that this is going to take a fairly long time. Reason being is because, let's put a little note here before we run this cell. Note, calling, even though we're running on a GPU, this is just like training our full model. So calling predict on our full model and passing it the test data batch will take a long time to run. And then it's going to be something like about an hour. We'll just go about 1 hour. That's what I found anyway. Reason being is because we have another 10,000 images here. And what we have to do is get our loaded full model, so all of the patterns that our loaded full model has learned in the training data set, it has to go through those, process the 10,000 images in our test file names or our test data batch, and then make predictions on those based on the patterns it finds in that test data. So we've set verbose equal to 1, so that when we run this, it's going to give us another little time step to update us about what's going on. So, without any further ado, let's run this and wait for it to load, and then we'll do the same thing again. I'll speed up the video so it'll be like instantaneously loaded for you. In reality, it'll take you a while to run this cell. In reality, it'll take me a while to run this cell, but I'm just doing it to show you it loading up, creating an ETA message, and then going through making some predictions on the test data. So we'll just wait a little while. This is going to go up. There we go. So ETA about 38 minutes. It has to go through 324 batches. And so that is because if you go 10,357 divided by 32, it's going to round that up to 324. That's where that number comes from. Okay, so I'm going to wait for this to go through. You might have to wait for it to go through as well. You don't actually have to wait. I'll be back in a few seconds. So I'm going to pause my video here and I'll be back in 3, 2, 1. And we're back. Now, I've gone and done something a little bit cheeky here. As you see, we've got about an hour left. But I figured, rather than me sit here and wait for this, I've actually, like any good chef has done, I've prepared a dish earlier. So I've actually gone through this process and waited the full 1 hour to go through. And now you could wait for yours to go through, but if you'd like to download a pre-made CSV of the test predictions, I'll attach that in the resource section so you don't have to wait that full hour to go through. And now I probably should have told you this before running this cell, but it's a good thing to sort of just get your feet wet and then figure out a better way of doing things. If we wanted this to save test predictions to a CSV file after it runs through, because if we waited a full hour for it to go through and then we somehow, our runtime disconnected and it didn't save, that'd be pretty disappointing. So what we can do is use np.saveText, this function here, to save, will this load a docstring while this is running? I don't think it will. But what this is going to do, oh, we forgot this, preds array. So let's just say that this finished. If I ran this cell after it, it's going to save test predictions, so this NumPy array, which is a prediction probabilities array, to this file as a CSV with a delimiter, comma, for comma separated values. And then once it was saved, it's going to appear in our files as a predsarray.csv because that's the file name we gave it. And then we can use np.loadText to load it back in. So what we'll do, rather than wait for this to finish, I'll just show you that in action. So these are some prediction probabilities that I've made in the past with a full model. So I'm going to stop this. Had about an hour to go. So again, my estimation is going to take about an hour is incorrect. So keyboard interrupt, there we go. So we're not going to run that because I've already saved this to preds array, but I am going to run this. So let's pretend I've run this after this cell has completed, so this ETA has reached 0. So I'm going to load in this array from a CSV file. Beautiful. Now let's have a look at the first 10. There we go. So these are all prediction probabilities for the 10,000 images. So let's have a look at the shape of test predictions. $10,357, so that's how many test images we have. And each one of them has 120 different prediction probabilities. Now we've seen these values before. And so, remember, I've just taken this, let it run to its extent, save the CSV to a file that I've done earlier, as if we've cooked something earlier, and then I've just reloaded it in here. If my runtime disconnected, I'd want this file to be saved somewhere that I can access it later. And so, what's our next mission? If we wanted to submit this predictions array to Kaggle, what would it have to look like? So the sample submission is here. Oh, something went wrong loading your data. That's not very fun. But luckily, I've got this file in Dog Vision, and it's a CSV. And so all I've done is I've just downloaded it and opened it in Google Sheets. So this is what it looks like. This is the sample submission. We need to get our predictions array into something like this. So an ID column, and then a column for each of the different dog breeds, and then their prediction probabilities. So that's what we'll work towards in the next video. We'll get our prediction probabilities array for Dog Vision, or we're actually going back to the Kaggle dog breed identification format. So we'll get it set up like that so we can make a submission to Kaggle with our predictions. We've got a predictions array, but now we need to get it in the Kaggle submission format. So that's what we'll be working towards in this video. Let's go make ourselves a little heading. Preparing test dataset predictions for Kaggle. And if we look at the sample submission, we kind of know what we need. We know we need an ID column, which is the file IDs from our test images. We know we need columns for each of the different dog breeds. And we know we need the prediction probabilities, which is what we've got at the moment. We've got an array with all of these numbers. We basically need to just set up our predictions probability array into a data frame like this, export it as a CSV, and then upload that to Kaggle. So let's write that down. Actually, we'll put a little link in here of what Kaggle wants. Evaluation, copy that. This is just what the sample submission has to look like. Looking at the Kaggle sample submission, we find that it wants our model's prediction probability outputs in a data frame with an ID column and a column for each different dog breed. Well, it's not really a data frame, it's a CSV, but we can be a little bit incorrect there in our wording. And how are we going to do this? Let's write ourselves some guides. So to get the data in this format, well, this is a testament to our favorite little graphic here of preparing inputs and outputs. So now we've worked with the inputs. We've saved and reloaded our trained model. Now we're making a bunch of predictions, or we have made predictions. We're preparing our outputs, more specifically preparing our outputs for Kaggle. We will create a pandas data frame with an ID column, as well as a column for each dog breed. And then we're going to add data to the ID column by extracting the test image IDs from their file paths. And then we're going to add data, the prediction probabilities, to each of the dog breed columns. And then we want to export the data frame as a CSV to submit it to Kaggl. This is what we're after. And probabilities is spelt wrong. Standard Daniel. Typo king. Some nice little full stops. All right, so the first step, let's go through and create a pandas data frame. We've had experience of this way back in the pandas section with empty columns. So we'll go preds df equals pd.dataframe. So just a standard nomenclature for a prediction data frame. Preds df, preds data frame or predictions data frame. Columns is going to be equal to ID plus, we need a column for each different dog breed, so we'll do one list unique breeds. And I just want to show you what list unique breeds looks like. List unique breeds. So there we go. So if we added ID to that, let's give that a burl. ID, oops, trigger happy once again, plus, there we go, ID plus list unique breeds. That is some column names for us. We'll comment out that, and we will check out the head of our preds.df. Should be empty with just a bunch of column names. That's what we're after, ID and all of our unique breeds in order. We've done this. So putting in some emojis. All right, add data to the ID column by extracting the test image IDs from their file paths. I believe we have already done that, but what we might do is just do it again. Test file names. But the way we can get each ID is by, we want to extract this out. So we could do a little bit of fancy regex on this, but I'll show you another way. Append test image IDs to predictions data frame. So we want to go test path. Well, did we already create test path? We did. Okay, wonderful. So let's get test IDs. So this is just the path to our test file. And test IDs is going to be equal to a list comprehension of os.path, and then what is it? Split text. I'll show you what this does in a second. Split text. And for path in os.listdir test path. That should be correct. How can I show you an example? os.path.splitText. We want to get test file names. 0. Will this work? There we go. Okay, so it splits off the last little bit of the path, but we only want this. So that's why we have to do it for just the test path. So we want to just go through this test folder. Now it's not going to show up here, is it? Because there's a lot of images in there. That'll take a long time to load in Colab. You're just going to have to trust me with what this does. Let's just see it in action anyway. Test IDs. Will this work? If in doubt, run the code. Alrighty. Actually, we don't need the JPEG bit. So what we're going to have to do, we only want the first element of each of these. So we're going to have to put a little 0th index there. And let's see what this does. That's what we're after, test IDs. I don't want a large printout there. So what I'm going to do is just go preds df. So I'm taking my data frame from up here. I'm going to make an ID column with the test IDs. So just taking that and putting that there. A little bit of overkill running this cell 3 times, but that is all right. Let's check out the head of our preds.df, as we always do when we manipulate our data. Okay, so we've got some IDs in there. Now we need to just append all of our prediction probabilities for each dog breed. Now how might we do that? I want you to have a think about this for a second. What do we have? We have test predictions, which is an array of predictions probabilities. And what do we have that's a list of different dog breeds? We have unique breeds. Of course we do. So add the prediction probabilities. This is getting exciting. We're getting so close to being able to submit our first full-blown deep learning model to Kaggle. We've gone from head to toe. The whole process, the whole shebang. If you can't tell, I'm pumped. So this is going to access the preds df of all of the unique breeds, so all of the breeds columns. And then we want to just set that, look how easy this is, to test predictions. Preds df.head. And we are done. Ladies and gentlemen, have a go at that. If we would compare that to the sample submission, of course this goes on for a lot longer, but ours is using the model we have built. The numbers are going to be different, but that's okay. Now let's export it to a CSV so we can submit it to Kaggle. How do we export Panda's data frame to CSV? We use to CSV, of course. We want to go drive, my drive. I'm going to go to dog vision, and I'm just going to save it as maybe full model predictions submission 1.csv. Or maybe we'll tell ourselves mobilenet v2.csv. And we don't want index. So index equals false. We'll go here. We'll just write what we're doing. Save our predictions data frame to CSV for submission to Kaggl. Is this going to save? Fingers crossed. Yes, of course it will. Now let's have a look in here. In our files. Oh, maybe we've glitched out. We've just saved a CSV there. Maybe Colab's lost the plot on us. Give me a second for my Colab window to reload, and I'll be back once I have access to this folder. Okay, I'm back. So sorry about that little interruption in broadcast. Seems my Colab window decided to go bonkers. You see why? Because I decided to open the test folder. I need to close that. And I might have to pause it again. 1 second. All right, third time's a charm. We are back. So be very careful with folders that you open in your Colab window. If they're full of data, aka 10,000 plus images, it will freeze up your Colab notebook. There we go, full model predictions. Well, we can't really see the whole thing there. Oh, there we go. And that's just our CSV file there. So if we wanted to, we can download that. We do want to. So we'll just wait for that to go through. I'll speed up my video until this is fully downloaded. Alrighty, so this is fully downloaded. All I did was just click download and then waited for it to go. It took about a minute or so, not too long. This is about a 30 megabyte CSV. If we come to my downloads folder, if we come here, yeah, about a 30 megabyte CSV. So 10,000 predictions. Now we've got that, let's go to Kaggle and we can go late submission because this competition has already closed. You can see my past one there 5 days ago. So let's upload. I want to show you that this works. Open. I'm just selecting the CSV we just downloaded. It's going to go through, briefly describe your submission. Let's go transfer learning, that's what we'll call it because that's what we used. Transfer learning, mobile, net, V2, dog, vision, baby. And then we'll make submission and it's going to score it. Now there's something up with this. Oh, 20. So that would be our goal, is to beat this one on the next one. And if we go back to the leaderboard, see where we appeared, we'll probably find public leaderboard. Score 0. I'd be very skeptical of any Kaggle competition where people have score of 0. So what you can actually find out is you can actually jank or actually hack the score here. So don't worry too much about submitting to here on a late submission. Your next goal is just to reduce your own score. And if you want my example submission CSV, I'll just link this in the resource section. You'll probably get the same score as me. Our next step in this project, if we were to keep extending it and train a new model, would be to beat our original score. Rather than paying attention to the leaderboard straight away, is focus on when you first begin, beat your own score. So now we've seen how to make full-blown prediction for the Kaggle competition. But that's not our original focus. Well, it kind of was. I lied. Right back up the top. What's this notebook called? Dog Vision. So our problem is identifying the breed of a dog given an image of a dog. When I'm sitting at the cafe and I take a photo of a dog, I want to know what breed of dog it is. So it's likely you'll want to be able to make predictions on your own custom images. So rather than just images that Kaggle has given us in a test and training set, what if you had some images of your own dog, which I happen to have, or a dog that you saw at the cafe that looked really cute and pretty, and you wanted to know what breed it was, so you took a photo and you came back to your machine learning model in this notebook, and you're like, I want to see what breed of dog that was using my model. Well, let's have a look at how to do that in the next video, making predictions on custom images. Alrighty, the most exciting part of dog vision, the reason why we built this in the first place, it's so when I'm sitting at a cafe or when you are sitting at a cafe and you take a photo of a nice dog and you come back here and you want to check what breed of dog that was, you can. So let's make a little section, making predictions on custom images. And this is just another version of processing our inputs, passing them to our machine learning algorithm, and then verifying our outputs. When we're first starting with machine learning, when we're first starting with deep learning, this is what we're focused on. What are our inputs? What are our outputs? How can we use an existing machine learning algorithm, which we already have, to figure these two out? So let's go here. And what do we need to do? So to make predictions on custom images, actually, let me just show you the custom images first. So I've got 3 dog photos here. There's my puppy. We've seen that one before. That's 7. Bella's actually in the background. Might confuse our model a little bit. There's another photo of baby Bella when she was so small. She's a lot bigger than that now. And there's a recent photo of Bella sitting on one of our couches, just chilling out, staring at the camera with those big brown eyes. This is a beautiful thing about working on a deep learning project that works with dogs. You get to look at photos of dogs. So get the file paths. We need to get the file paths of our own images. Oh, actually, my photos are currently stored locally, so we might need to upload them here. Actually, what I'm going to do is create a new folder. While I'm uploading these images, I want you to think about what do we have to do to the inputs of our machine learning model. My dog photos. What's the most important thing when we're preparing our inputs? Well, if you said we have to convert them to numbers, you'd be correct. And if you said we have to convert them into the same type of data that our machine learning model was trained on, you'd also be correct. Turn the file paths into data batches using create. Oh, this is where our function is coming back into play. Create data batches. Yes, and since our custom images won't have labels, because that's what we're trying to find out, we set the test data parameter to true. And then we pass the custom image data batch to our model's predict method. And then we have to convert the prediction output probabilities to prediction labels, so making them in something that we can understand, and then compare the predicted labels to the custom images. Whew, that's a bit of a challenge, but it's nothing that we've seen before. It looks like a lot, but we're going to take it down. So let's get the custom image file paths. We'll set up the custom path. And we just did that, so that's going to be drive/my drive/dog vision/ what was it, my dog photos. That's where I just uploaded 3 of my own dog photos. So you might want to upload your own dog photos to here if you have some. I hope you do. And then we go here, we're going to go custom image paths equals a little list comprehension again, plus fname file name for fname in os.listdir. So this is like the gold standard of what you're doing with your machine learning model. Once you've trained it, it's one thing to use it on data you've been provided, but what we're doing now is using it on our own custom data. Oh no. There we go. So we should have some custom image paths. And what was I saying? This is, the gold standard of machine learning and deep learning is seeing how your model... I can't even type right now. Why hasn't this work? For SF name in dog vision, custom path, plus fname for fname in OS. Why isn't this working? Oh, do I have to rerun this? Empty list? os.listdir custom path. Have I not uploaded any dog photos there? That is why it is not working. Classic. Let's upload my doggy photos. Got distracted talking, too excited. Open that. So this is gonna upload. Shouldn't take too long because it's only 3 photos. If you were using more data, I'd probably find a different way. There we go. Now we'll come back here. This should work. Fingers crossed, and it does. Now, what do we have to do? Well, we need to create data batches. So this is what we can do. Turn custom images into batch dataset. So we'll go custom data equals create data batches. This is our trusty little function that we've written many moons ago, but as I said, it's going to come in handy one day. Custom image paths, we'll pass that there, and then we'll check out custom data. Oh, remember, because this has no labels, we need to pass it in as if it's test data. There we go. Batch data set of the shapes. There we go. Images 224 by 224 by 3 in the form of TF floats. Our custom images are in tensors, so we can make predictions on the custom data. How do we make a prediction with our model? Custom preds loaded full model dot predict custom data. Yes, please. We'll have a look at custom preds. Can you guess what shape this will be? Ah, we've seen that before. We're getting hot. We're getting hot in here. Custom preds, yes, 3 images. So we've got 120 prediction probabilities for each one. And now, what do we have to do? So now we've got a prediction array. Let's convert them into labels and then compare the labels with each image. So get custom image prediction labels. And we've got to go custom pred labels equals. We're going to go get pred label. Wonderful. Pass it custom preds. I for I in range len custom preds. Now this is just a little comprehension to get the prediction label of the custom pred I for range length custom pred. So for each one, get the pred label. Custom pred labels. Oh, we are kicking. Have a go at this. So now we need to get the custom images, aka unbatchify. Oh no, our unbatchify function won't work since we don't have any labels. That's one little tidbit that we could probably improve our unbatchify function later on, but for now, we will get the custom images. Our unbatchify function won't work since there aren't labels. Maybe we could fix this later. Because we're on a roll. We don't want to stop while we're hot. We don't want to stop. Dog vision is coming to life. We're like mad scientists here hacking together. We've gone home from the cafe so distraught that we've built an entire deep learning model to help us figure out what dogs we're checking out. For image in custom data, we just need to unbatch it. So we'll go unbatch. So remember, this is going to unwind our data batch into just images and into something that we can iterate over because we're using as NumPy iterator. So custom images dot append image. Does that make sense? So we've got an empty list. We're unbatching our batch custom data set. We're turning it into an iterator and we're appending each image to custom images. Shift and enter. One last cell, I reckon. Check custom image predictions. Now we want to plot it up. We want to plot it up like we've done before, right up here. But because we don't have labels, we can't really use our function up here. That's a bit of a boo-boo. So we might have to refix this function at a later date as well. That might be a little challenge for yourself. Now we go right back down to where we were. Check custom predictions. plt.figure. We're going to go fig size equals 10, 10. And we're going to go for I image in enumerate custom images. So if you're not sure of what enumerate is, it's just going to go for the images in custom images, count them up, save the count of it to I, and save the image inside custom images to image. And we're going to go plt.subplot. We're going to go 1, 3, I plus 1, 3 columns, 1 row, and this is the index of our subplot. That's why we get I. And we want to go plt.xticks, set that to none to get rid of that yuckiness. We just want to see our pictures in their full light. plt.yticks, plt.title, custom pred labels, I, plt.imshow image. So the title is just going to be the label that our model has predicted, and the image should come up. So are you ready? Dog vision in the flesh. Oh, how good is that? So this is a picture of baby Bella, Lakeland Terrier. I'm not actually sure what a Lakeland Terrier is. I think we have looked that one up. Images. Okay, you can kind of see why it looks like that. Because Bella, in baby form, is real fluffy around here. And then that's 7, Golden Retriever, which is exactly right, what she is. And Bella is a Labrador Retriever. That is phenomenal. So dog vision has fully come to life. You should be ecstatic with yourself if you got to here. Now, I need you to do me a favor. If you're in the Discord chat and you've made it this far and you've made some predictions on your own custom images with your dogs, please share them. I want to see your dogs and what our model that we've built has predicted for them. And is it right or is it wrong? Maybe you could add that to this functionality. You could make the name, because you know the true labels of your own dogs, or maybe you don't. So maybe you're trying to figure it out. That's the purpose of dog vision. That was our end goal right from the beginning. So if we come here, we've gone, look at all these headings. You should be so proud if you've made it all the way through here. We've gone from right up the top. This notebook builds an end-to-end multi-class image classifier using TensorFlow 2 and TensorFlow Hub. We've defined our problem. We've defined our data from Kaggle. We've defined our evaluation. We've gone through a bunch of different features. We've got our workspace ready using TensorFlow 2 and a GPU. We've got our data ready, turning it into tensors. We've seen how many different dog breed images there are. We've got the images and the labels. My goodness, how much have we covered? Go back through all of this and give yourself a pat on the back. And if it all doesn't make sense, don't worry. If you've gone through it for the first time, it's not going to. But what this is, it's a momentum builder. Let's go right down to the bottom. What we've done, we've gone through, we've got our data ready, we turned it into tensors. We've picked a model to suit our problem, image classification, using TensorFlow Hub, aka a neural network, a deep learning neural network. We fit the model to the data, we've made predictions, we've evaluated our model by visualizing our predictions, we've improved through experimentation by trialing out a model to make sure that it works on 1,000 images first before scaling up. Of course, there are some more improvements that we can do. I'll leave that, some extensions in a lecture after this one that you can have a look at. And we've seen how to save and reload our trained models. Woo! That is phenomenal. You've made it through. Holy goodness. I am so stoked for you. The important thing is to remember that this is a momentum builder. You've now gone through a full-blown end-to-end machine learning modeling task. You've gone through these steps, a TensorFlow workflow. So now you can adapt the principles that you've learned all throughout this notebook on different problems. You can go, hey, I know if I'm working on a different problem, I might not know exactly how to solve it, but I've got evidence that I have actually been end-to-end on a problem that I hadn't seen before. I've got a set of data, I've turned it into tensors, I've trained a model on a GPU, I've made predictions on test data, and then I've made even predictions on my own custom data. You should be stoked with yourself. So please share your predictions on your custom dog images if you have them. I would love to see them. Make sure you tag me in the Discord. But otherwise, I will see you in the next video, and I'll leave some extensions for this project as well as different resources in the next lecture that you can check out.